Hello, hello, I'm audible. Hello, hello.
Good morning to everyone. Welcome back to the third day of GIAN Course. We are now ready to begin lecture 6, which will be delivered by our esteemed international faculty member, Professor Sukumar Kamalasadan. Sir, we are truly honored to have you with us. We look forward to learning from your vast knowledge and experience. Please, sir.
Let's start, right? Start. Okay, so we'll start slowly. I think many are coming, I guess, because of the weather. So what we will do is we will try to start looking into, like I was mentioning yesterday, uh, parts related to stability, reliability, how you can manage IBR to improve stability and reliability of the electric grid. So far we have learned how to model an electric grid and how to do power flow models of electric grid, which we did learn on transmission system, distribution system, and then we said, okay, this power flow model you can run. So power flow model you can run in the form of snapshot. So you can run the power flow every 15 minutes, every 30 minutes in operation, right? Normally power flow is used for, we say it's used for planning purposes, meaning you can use a power flow to design an electric grid. Where do you need to improve the voltage, right? What do you get from power flow? You get what? Voltages, yes. You get the voltages and angle of the voltages from power flow. So you know what voltages are. You can actually see what are the losses in the system. You can see how the power goes from the generator to the load. In the distribution system, you are more interested in losses and more interested in voltage. In the transmission system, you are more interested in how to generate generator scheduling, how many generators are connected and how do you schedule the generator to supply power, those kinds of things, right? So we know how to run a model of electric grid through power flow. That model of electric grid through power flow you can run to design electric grid, right? Same electric grid power flow model you can run when the electric grid is in operation, meaning every 30 minutes you can run this power flow, right? So if you, good morning. So if you run the power flow every 30 minutes, what happens? If you run the power flow every 30 minutes, what happens? You will be able to see the voltages of electric grid when the load changes, right? Because every 30 minutes or every 10 minutes, 15 minutes, the load keeps changing. So the load keeps changing, you can run the power flow again, run the power flow again, you can run the power flow again, right? Such power flow running every 30 minutes is useful for electric utility. Why? Because you can now know what are the changes in voltages in different points when the load varies. The load variation is very slow varying load, right? In the morning you'll have a peak, maybe sometimes, and in the evening you'll have another peak. Depending upon the duration of the weather, you'll see the changes, right? Such power flow study used by utility, we call it snapshot power flow study. Remember yesterday we talked about snapshot. Snapshot meaning one time you do the power flow, next time you do the power flow, you can do that power flow and then run as a snapshot study, right? Now we started working with time. Okay, yesterday afternoon, so okay, snapshot I can do every 30 minutes. When you say, oh, in between 30 minutes, what happens? Is there something changing? If that changes happens, can I include that in the power flow? if you include those changes in the power flow, it's good for me. I can really exactly know what happens on the system. So then we said, well, you can now move from steady state into little bit quasi steady state or time dependent, power flow or time series power flow. So our first step was to see what are the slow moving devices. So how you capture a model on slow moving devices and understand the grid. So yesterday we started looking at one slow moving device which changes the voltage, which is a controller in the electric grid called tertiary control, which is changing the voltage by changing the tap of the transformer. So we said, oh, transformer is going to change the voltage. Can we include that changes in the transformer voltage in power flow and then rerun the power flow, right? For that, you need to model the controller of the transformer. And if you model the controller of the transformer, I can see the voltage changes that happens in the transformer. And if you see that voltage changes that happens in the transformer, I can include that voltage change and then rerun the power flow. Such power flow models are known as quasi steady state power flow. Okay, quasi steady state power flow, quasi steady time series power flow, okay? QSTS. So quasi steady time series power flow is useful if you want to include changes, slow moving changes. So then we discussed, oh, okay, so we have a voltage regulator motor controller you can include. Can I include any other controller, which is slow moving? Yes, any slow moving controllers can be added into the quasi steady state time series power flow. For example, battery. So for example, battery pushing the power and battery pushing the power based on set points, slow. You can include that. So having said that, we looked at the quasi steady state time series power flow. For running the quasi steady state time series power flow, we looked at a power flow model which is different from forward backward sweep. Okay. So what we did was we looked at a model based on current injection or current sensitivity based model. So what we did was we tried to introduce you yesterday. It was a little late in the game yesterday and everybody was tired. So I am going to reintroduce you that for first 5 minutes or 10 minutes, which is the power flow model that you can run the electric grid. There are 2-3 advantages for this type of model. One advantage is that this is sensitivity based, which means if there is a change in the voltage with respect to the change in the power, change in the voltage with respect to the change in the reactive power, those sensitivity or those changes you can capture. That sensitivity in a transmission network we normally capture. And that sensitivity based power flow and transmission network, whatever we capture called the change in the voltage with respect to the power, we call that as a Jacobian. So Jacobian is the first course in power grid or power system. When we did in undergrad courses, we will learn what we call that as sensitivity. So group of sensitivity of several parameters brought in the form of a matrix is called Jacobian. Okay. So changes with respect to one variable and changes with respect to the other variable. That is not changes with respect to one variable with time. So it is not a derivative with respect to time, but it is a derivative or partial derivative with respect to variable, and that's why we call it sensitivity. So difference between a sensitivity and a difference between a time dependent variable or time derivative is that in sensitivity we are looking at what is the changes with variable with respect to state or variable with respect to variable. Yeah? So having said that, this approach you can bring that. In the forward backward sweep, we don't do the sensitivity for the entire power grid. We do the sensitive or change only the voltage drop in every system. So calculate the load, then you calculate the, remember, we calculate the voltage drop, then you calculate the voltage. That's how we do it. So first what I will do is I will show you this power flow algorithm comparing with forward backward sweep. We just did it one small, I think 5 minutes or something yesterday. So I'm just going to repeat that and then show you. So this algorithm, like we discussed yesterday, can also include every aspect of power distribution system, including untransposed line, multi-phase laterals, all these names you know. Okay, everybody know untransposed lines? What does that mean? It means the lines are not, transposed or switched. So what happens because of that? There will be unbalances between line to line unbalance. Okay. Multi-phase lateral, you know what that means? Remember, there's like a tree, a tree comes and then you have laterals. Step voltage regulator, same as distribution voltage regulator, that's included. Zip load with star and delta connections, you have Y and delta connections for the load. Different transformer types, shunt capacitors, and we have the IBRs sitting here, which are two different type of modeling of IBR we have done so far in the power flow. What is the first model we call it? IBR acting as a PQ type. What do you mean by IBR acting as a PQ type? Every IBR, when we talk about, our interest is only on the inverter. Remember? So IBR acting of PQ type means what? This inverter is not delivering any reactive power. It is actually keeping the reactive power or a power factor constant at whatever number. It could be 0 or it could be 0.5 or something. So it is going to be just staying there, pushing the power from sunlight or whatever to the electric grid. Such a model of a DER is called PQ type. Okay, it's also called negative load model, which means the P that is coming into from the DER, if the load power is positive, you see the power from the inverter is negative, or the power from the PV farm is negative. So this model will be used also to represent what we call it as a net load. What do you mean by net load? Generation minus load. Remember, net load. So if the net load is a negative, we call that as generation. And if the net load is positive, we call that as a load. So that is a representation, which is a very basic representation of the inverter with connected to energy source. So you can consider that as like a voltage source or a current source, and you can develop that as a model. What's the next type? Next type, you will use the inverter as a PV type. Oh, so now the inverter, which is basically IBRs, are now much like a what? Huh? What is PV? PV type means generator, much like a generator. Synchronous generators are represented as PV. Remember PV bus, So this IBR will now become a PV type. So how do you make an IBR a PV type? Well, you make a constant power coming off from the IBR, right, and control that power with the help of the PV farms or with the help of MPPT or with the help of battery connected to it. You control the power. What is the voltage? How do you control the voltage on the IBR? You control the voltage on the inverter side. So you actually, remember we said that reactive power is equal to square root of S square minus P square. You have a capacity you can define. Within the capacity, inverter can push or absorb the reactive power to maintain the voltage. So these are the two models. Remember these two models? We have developed these two models and studied these two. So now, if you want to run this type of power flow, you have to develop the Jacobians. Okay, Jacobians. Remember what is a Jacobian? We just mentioned about the Jacobian. This is a change of the variable output in a reactive power with that. So the Jacobian for a radial system, for electric distribution system is pretty simple. So if you look at a one phase, remember it has 3 phase, right? So there will be 3 inductance, 3 by 3 matrix, all the story we talked about. So, but I am talking about only one phase. So just to give an idea what that. So the impedance on one phase will be 2 by 2, right? So impedance on 2 phase will be 4 by 4. So you 4 elements. So that's how you have that 9 elements which comes for all the 3 phases. So this, when you look at it, if you divide them, the Jacobian, you'll get Jacobian like this. Okay. It is a pretty simple way. What is a Jacobian? You have to take a derivative with respect to the variable, partial derivative with respect to the variable to R. So it's a little tough if you do a long equation and then non-linear equation, you got to find the derivative. Here you can actually just put that box in here to find the Jacobian. Good. So that's the current injection. Now what is our algorithm? How do you do the power flow using this algorithm? This power flow using this algorithm is not that bad. It sounds a little bad, but it's not that difficult. I'll tell you what it does. It actually looks at the current mismatch on every point. Okay, current mismatch on every point can be represented as power divided by voltage and power divided by voltage plus V square over Z. So let us look at this word here. This power divided by voltage is exactly what you did in forward backward sweep. Remember that we said voltage divided, S load divided by V 2400 angle 0. So it's exactly what is being done. And what is this? Vi divided by Z. V divided by Z is basically the current, drop. So if you add the power, the current in here, so you can get the deviation of the current with the help of this equation going here, and calculated value for every bus, you can get the deviation of the current. So instead of calculating the voltage drop, which we did in forward backward sweep, what we are doing is we are calculating the mismatch in the current, and the goal is to reduce that mismatch and make it 0. Okay. How do you reduce that mismatch? Well, if you know the mismatch in the current, you can use this Jacobian and find the mismatch in the voltage. Now, once you know the mismatch in the voltage, you can update the voltage of the bus. Is this what we were doing in forward backward? Yes, this is exactly what we were doing in forward backward sweep. What were we doing? We were finding the voltage, and we said that 2400 is no longer 2400, it's 2350 or something. And then we said, oh, okay, now that's going to, I'll update my voltage to 2350 and do it. Same procedure, except that done in a little different way. So we were talking about it yesterday. The approach, difference in that approach is basically the modeling, capability, how to utilize that approach. So if you do that, you can update the voltage and you can repeat the process. So now I'm going to go with the flow chart. The flow diagram, it says that you compute the load, compute the active and reactive power, find the mismatch, update the mismatch with respect to the voltage, and then redo it. Okay. So I will be giving you a small example. I'm not asking you to do it by hand calculation. I'll give you a small example in MATLAB, so you can actually use that, and that will be like a homework assignment for next 2 days. So you can run this and then get acquainted with that. So this is basically some test. Oh, then we said something interesting yesterday. If you are going to model this on a power grid, what type of power grid models you will need, and how do you verify these models are good or not? Okay? So there is a standard library developed by IEEE for the power grid models. These models are called test library from IEEE. For a IEEE, any IEEE transmission and distribution network, this test library is available. Okay? This test library power grid models are real life power grid models, not that is artificially created. But the real life power grid model is, we call it massaged, meaning these power grid models are not exact number because that will be real life. So it's some confidentiality and things like that. So you can aggregate and reduce it with the same property of the electric grid. You give different bus names and then, hide some of the variables, and then models are ready. Okay. So these models can be used, and you can get this model from a web. If you Google IEEE test library, you have a test library, you can get these models. So these models are coming in this category: 4, 13, 34, 123, 8500. What are these? 13, 4, those things, what are they? Nodes. So in distribution system, we will always call nodes, which is basically, you already talked about the story of bus and nodes. So we covered from all the way up to, so you should be knowing now. People nicely calls buses too, but it is actually 13 for 34, 123, instead of bus, you generally call as node. Okay. So nodes associated with the system. So why do we need 8500 and go forward? Because scalability. We have to test the scale. Okay. Now the results has to be benchmarked, and these are some of the things benchmarking for that. Okay. Having said, when we do this benchmarking, you will be benchmarking with respect to the voltage, and the voltages will not be like a line, it will be discontinuous. You know why it is discontinuous? Because there are laterals that each laterals are ending in the last point on the electric distribution. So there are several endpoints in the electric, and these endpoints are not connected because they are all lateral. So your graph will be looking something like this, and you can compare that with the deviations of that with other algorithms. So this is what we call benchmarking. We also talked about scalability studies, testing. So you can do that on this graph. So you can see percentage error. You will look at what is the percentage error between each phase. Oh, by the way, when you plot the voltages on electric distribution system, you will have to plot it for every phase and see phase voltages are matching because there are unbalances. So that's a challenge on electric distribution system model. Good. So I just wrapped one more round review on what we have done. So you can actually compare this with a few different methods. This is a method that you can apply in distribution system also called Newton-Raphson. And this is some method that you can do current injection and then you can run it. The good news about current injection, this current injection model can be used to run for transmission system too, which means that you can make one power flow for transmission system and the distribution system, even though it is a little difficult. These are some, okay. So it's good so far, right? Now you can also run this model, same power grid power flow model with DERs. Okay. So this is an example test case when the DERs with voltage control capability are connected on bus number 3 of 123 bus system. What happens to the voltage? Now you see this no PV voltage and with the PV voltage. So this PV with PV voltage, this voltage is pushed up, and you can see that it's pushed up, which means that this voltage on the low points are, going up, and the low voltage on the high points can go down. So this voltage reduction, conservative voltage reduction, all those things you can actually study with this model. So is this a slow moving, changes in the voltage for the PV? You can actually add that and you can run it for multiple. This is actually a snapshot for one. This is phase A. This is phase B. Now with PV, you are pushing this voltage down now. You see this voltage was up and that voltage is pushed down by the PV controller, which means it's now close to 1. 1.0, 1.05 is very high. When you go look at the voltage, it pushed down. And, with PV, you are actually bringing this voltage back in here. So you can actually look at the bit points and you can control based on the bit points. Good. So that is just the summary. Now, I wanted to mention briefly about how you can run the power flow integrator. I think we talked about it in the one time, and I just wanted to bring that back up again. So if you want to run a power flow for transmission and a distribution system together, ideally you will see transmission systems are like this, distribution systems are connected. So what you do is you exchange the power from the distribution system to the transmission system, run the transmission system model, and after you exchange that power, you run the transmission system, get the voltage on the distribution system head end, run the distribution system model back again. Okay? So this is what we call it as decoupled power flow approach, which means you are running it in tandem. You are not doing anything together. You are not running or developing anything together. You run one, you get the result, and then you run other. Now, when you run this, will you be running in multiple iterations? Yes, you will run in multiple iterations. Come to a point that errors are minimum. You take that number and run this in multiple iterations. Come to a point. So, when do you know that this whole one, when do you stop for the whole thing? To know when do you stop for the whole thing, you look at this voltage at that bus which is connected and see for this loop, when you keep running, whether that voltage before and the next time is the same or if it is very close. If that is very close, we say that, well, you are come to a good point where you can actually have them connected. So, if you do like that, then this whole loop is complete. This method is called decoupled method. This method is not very accurate but this method is good enough in a compromise between accuracy as well as the trade-off, rather accuracy as well as the time, because this takes some time to run it for. Good. So now I'm going to talk about there are some problems with respect to this. So if you are actually having time delay for data exchange, data loss, simulation time step, all those things can make this approach diverging, you know. And the power flow, there is a challenge for the power flow. The power flow that you run on a transmission system is run on a single phase, which single representation on positive sequence. Okay, power flow that is run on a distribution system are 3-phase on a phase sequence. Okay. So you may want to say, how do I run this sum together? Will you run it in one phase, or will you run it in positive sequence representation or negative sequence representation? Okay. So that is one thing. The second part is, how do you benchmark this algorithm? If it is running together in closed loop, how do you benchmark? Well, the only way to benchmark is to have something which is completely together, the transmission distribution system together. You don't have, if you don't develop something like that, the only place you have is simulation models. Simulation models is in Simulink or in EMT solver, EMT type of simulation that you need to have, then only you can actually run. Otherwise, you cannot run. And the challenge with respect to 3-phase representation of transmission system and sequence representation for the transmission system and phase representation for the distribution. So what we can do, there is another challenge. Another challenge is, in the transmission system, there will be several distribution network connect. So if you look at a transmission system load point, you will be seeing 50 megawatt plus 35 megawatt. 50 megawatt will be 5 distribution system of 10 megawatt. Will you connect all the 5 distribution system, which is the 7,000 node or 5,000 node, and connect that to the transmission system, which is 35,000 node going into one point on a transmission system, which is huge? Or will you get an aggregated distribution system, one in detail and the rest in, comparable, whatever the total point, and then add? Okay? So that's basically the complexity. So it's important to understand that the distribution system cannot just directly connect to the transmission system and run because of the computational complexity. All voltages. The load being balanced for the transmission. So that is another challenge. You cannot, you cannot run it because it's unbalanced in nature. So to avoid all that, there are methods, and I'm going to talk about that method. So the first method is your representation of the distribution system. Representation of the distribution system for a transmission system. So if you look at the representation, there are 2 types. One is, we call it as that actually takes care of the things which you're talking about. One we call it multiplying factor method, another one is non-multiplying factor. In a multiplying factor method, what you do is, first we can get a per phase multiplying factor, which will not take care of the unbalanced nature of the distribution system because it is per phase. You can actually have a 3-phase multiplication factor with balanced shunt load compensation. So what we are doing is, we are actually putting the unbalanced distribution system and we are compensating that with a shunt load, which is a balanced shunt load. So all the load, look there, it's all unbalanced, but the total which is going into the transmission system, you will see that as a balance. You can do a 3-phase multiplying factor with unbalanced shunt load configuration. This will be completely 3-phase. So you can actually see all the unbalances coming onto the transmission system, not partially. Here it is only partial, here it is the full. So you have 3 different options. You can actually say, this is less unbalanced in distribution system, I don't have to worry about it. Or you can do partial unbalance, or you can do full unbalance. So, and again they are aggregated unbalanced, because it's the three phases are aggregated unbalanced. So you can use the multiplying factor, and there is another way which is non-multiplying factor. In this case, what you do is every distribution system is considered like that. It's not only one and then multiply with other. One distribution system, second distribution system, third distribution, all are like that. And then you compensate whether it is balanced or unbalanced or little bit confusing, right? Right? No? So I'll explain. So this is the first one. I'll not explain all 7. It's a little difficult to explain all of them. So the first one is the per phase multiplying factor method, which is via M1. We say, if you may recall, in explain 7. So this is a transmission system load, 14.9 plus 5J. This is a distribution system load. Each of these phases are unbalanced, which you can see. And the total is 3.62 in 1.45. What you do is that each of these phases, you do a multiplying factor and then make 49, 14.1 and 5. So when you do 14.9, it's exactly the same, but each of the phases are different with respect to the power, and the multiplying factor that you actually calculate is found separately for reactive and active power for each phase. And you will see the transmission system is balanced, but each of those phases the power are unbalanced. So you can actually get a multiplying factor. For example, you see 4.96 and 1.66 adds up to 14.95, 14.9 and 5. This 4.96 is coming with a multiplying factor. Each of those multiplying factors are different. You see? So you can actually do the multiplying factor different. So every phase currents are different, but the total seen at the transmission side is the same. Are you following? Yes, partially. Understand, right? It's understood? Understood? But yes. Not fully. Do we want to repeat it one more time? Okay. So what we are doing is, do you understand the transmission system load that is seen by the transmission? Do you understand the distribution system load which are unbalanced, right? You do multiplication for each phase to bring it to 14.9. So each phase are doing multiplication. Pretty simple. So 14.9, when you divide it, this is the number you get for each phase, right? So you take the multiplication factor, multiply with this 1.49. So you take this 4.96 and divide it by 1.49, you will get this multiplication. And you put that multiplication factor. They are all different, by the way, you see. And then you add them. So what is a shunt load? This is fully balanced, by the way, which means that the transmission system will not see any unbalances on the distribution system. Very simple method, but it will lose the challenge associated with unbalance. It will not come. That is why the shunt load is basically 0. See, there is no shunt load which is acting. Make sense? Okay. Now in the next one, we decided, well, we want to see the unbalances on the transmission network. Okay. How do you get unbalances on the transmission network? We will keep the unbalances of the distribution system just like that. You see? After you keep the unbalance of the distribution system just like that, you will get the total value 10.89, 4.36. They are all unbalanced on each of the system. Okay. How do you get that unbalance represented on the transmission system? You put a load, that's a separate load, shunt load. You see, this shunt load, what you are putting there are actually a constant load, and that constant load keeps all the unbalances there, and that all unbalances add up to 14.9 and 5. So the whole unbalance is going, but total is 14.9 plus 5. So the transmission system will see that same load, and then it can run the transmission system. But every phase unbalance is going into the transmission network. So if you run a transmission network with positive sequence, you will not see any unbalance. If you run a transmission system positive sequence, negative sequence, 0, you will see all the unbalance which is coming. So you have a choice whether you want to use all the unbalance and run the power flow or not. You can actually do either one of them. You have kept the provision. Now this shunt load, what you are seeing, this shunt load 1.34, 1.5, they are all balanced, right? So this system is, following. Make sense? Little bit over there. I'll take 2 benchmark points and then I will say if both of you are okay, then I will move forward. Otherwise, we'll learn. Is good? Okay. Now you can also do this also unbalanced. So you see right here, this shunt load, what you're seeing is all unbalanced. This is the full unbalanced case in which now every distribution network, whole unbalanced is seen at the transmission network, even though the total is 14.9 plus 5. So now you have a choice what you want to do. You want to do the full. So this compensator which you are using as a shunt, you are making it balanced or unbalanced, and you can actually map it accordingly. In none of these cases, you are not putting all distribution system full. You are putting only aggregated one distribution system, and then you can actually do the whole thing again with the whole distribution system connected. So you have more options which we can. So that is one, and then you can actually repeat this with the whole distribution system. So this is a 4, 5, 6, 7, which I'm not going to go in detail. You can actually do each phase. You can connect it with different values and then apply, different. But you got the idea, right? So, you got individual distribution system connected and you have a compensator. You scale it up, multiply it, scale it up. In that compensator, you can add 3, 1, 2, and then adjust this. Good. So the next part I will talk about, can you run this unified power flow? Can you run this TNT power flow without decoupling? Yes, they can put dynamic compensator. You can do a very important point. So yes, so this whole thing we are talking about snapshots. So we are talking about just one shunt compensator. You can put that and then connect it. You have the flexibility of looking at the unbalanced nature of that point with respect to time, depending upon how you define the time, and then you can change this compensator to compensate for that unbalances at that point. So that is basically going to be dynamic, with respect to. So how do you compensate for the unbalance? Well, you will be able to compensate with respect to the voltage. If you have dynamic compensate, you can compensate with respect to the voltage at the point, and then maintain the voltage balanced, right? Or you can actually add shunt reactor. So physically you can do the same thing what we are doing in modeling world. In fact, if you increase the dynamics and you do more, depending upon how they're unbalanced, you can also do reactive compensation using power converters. It's maybe fact devices or even the inverter sitting at that point. So so that approach is flexible with respect to time. You can actually adapt based on it. One other part is very important is, okay, now we have it decoupled, right? Can you make this combined, meaning one power flow that runs for the transmission system and the distribution system? This is generally known as a unified approach or unified TND power flow modeling. What you do in here is to run this whole power flow model in one algorithm or one method. So if you do that, you will be representing. You have some challenges. Okay, the first base challenge is, okay, how do you run a power flow? What is the base first thing which you need to do if you run a power flow? Yeah, but what value? What is the first thing which you need to do to run the power? I'll give you a hint. I'll give you a hint. Okay, you look at this equation. This equation needs to be solved if you want to run a power flow. Yes. Okay, let's look at this equation. V equal to summation of y times I, right? Or the other way around. Z times I, or V equal to. So what is important? Before you find V and I, what do you need? Y. is the first thing what you develop in a power flow, and we call in a transmission network power flow is called Y bus. So without having a network, you cannot solve anything. That network development is required. Now let us look at it. If you are coupling two power, meaning you are making unified distribution system and transmission system, what do you have to do? You have to make one single impedance matrix connecting the distribution system and transmissions. Now look at what is the impedance line representation in transmission system. One simple reactance or a resistance. What's the line representation in distribution system? 3 by 3. So this big matrix which is sitting there at 3 by 3. So that is the first challenge. Okay. If you solve that challenge, most likely the algorithms may converge. Algorithm may come back. So how do you solve this unified power flow? So I'm just going to talk about few things. So in the transmission network, you have a power equations, and a distribution network, you have a power equations. So the unified voltage equations will be the unified voltages, transmission network and distribution network, unified power, transmission network and distribution network, unified current and unified reactance. Right? So then you have to put it in one matrix and you can solve. To solve it, you need a unified Y. Okay. So I'm going to spend some time on how do you do this unification. Maybe with a small example. So what you do with the unification is you are going to, let's say this is a transmission network, and these are two distribution network connected into two nodes on a transmission network. Okay. So if you were to connect these two distribution network, two nodes on transmission network, you first look at which node they are connected, node 4 and node 8. Second, you look at what will be the number of nodes in each, 4 and 3. And then you are going to look at combining the which points you are connected and the nodes. So 4 and 8 with 2 and 3, these two nodes. So this will give you, it's more like a address mapping in computers, where you are going to use a stack register and you're looking at where the points are, the address of that point and how many are there in the row. So you add them together and bring them in the form of a matrix, and then you will see, for example, bus vector, position vector, and tie line vector. So this tie line is a connection point where the distribution networks are connected to the transmission network. This is one approach. You can do other approaches too.
So that is when we are considering the radial topology of the distribution. So when controlling the voltage for radial system, suppose which voltage we have to control, because the radial system at one point, suppose it is connected to the plasma system. So at this node only we have our lateral node we have to.
So this is how it works. Very good question. So this is how it works. All the time, the transmission system output, which is the head end we call it, or the node the distribution system is connected, that voltage is the first point that you kind of maintain. And you maintain that voltage based on the entire electric grid load, including the distribution grid load and the transmission system stability. And you maintain that voltage. Most of the time you maintain that voltage with in limit 1.05. You cannot maintain 1.1 basically. That's the max which you can do. That is the source side of the OLTC, LTC transformer, source side of the transformer. So you maintain that voltage. So when you run a power flow, your job is to run the power flow to maintain that voltage at that point. But before running combined power flow to maintain the voltage at that point, you want to make sure that for any given voltage on the source side of a distribution network between 1 and 1.1, the whole distribution voltages are that you will do with a distribution power flow or distribution. If the distribution voltages are not good on the distribution network, you will put LTC and you will put regulators. Remember that slope which we talked about, right? So you maintain that slope proper. And you wanted to make sure that this slope, when this shifts, if you may recall, then we draw two lines, parallel lines, right? So the parallel lines are actually the voltages set by the source of the substation. See, 1.05 to 1.1 to 1, the voltage can vary, right? With all these time, the distribution should be working well. So you'll put the voltage regulator and transformer on the distribution line is working well. Then you take that distribution system. For this power flow, you don't really worry about voltages in any of these points. You only worry about voltage at that. And why do you want to run? Oh, now the next question, that's a counter thinking, right? Why do you want to run this power flow? I already maintained that voltage proper. I know it's 1.05. Well, if it is 1.05 and with that load, is that whole integrated system stable or not is something that we are testing. Especially with DR, because otherwise it's mostly stable. It's nothing which is, makes sense? That is the idea here. So once we develop this, this battery is low, so maybe that's because it's. So with that, what we will do is we will just connect the Y bus and develop that Y bus and then add the tie line Y. So if you add that Y bus and add the tie line Y, you will get a Y bus like this. Okay. Now this Y bus has, you see these blocks are transmission system and distribution system Y. So let's assume this is a 3x3 transmission system. You'll have a 3x3. You see? So this 4, 5, 6, 7, you'll be having a 4, 5, 6, 7 matrix. 3 will have a 3 and the rest will be all 0. Okay. And then you will have this cross or X value is for the tie connecting points. So this X value is tie line correction. So if you write this Y bus, you will realize that this power flowing through this Y bus, this point needs to be based on that this tie line point needs to be added. Otherwise, it cannot solve. So we'll go with these added tie line points. So if you look at this tie line 2, 2 is this point, and 2 basically right here 2 to 4 is connection between these 2 points. 4 to 2 connection between that and 4 to 6. So these are the 4 points that come as a tie line. Similarly, in here 8 to 3, so you'll see 8 and 3, and 8 and 8, and 3 and 3, and 3 to 8. These are the diagonal element and diagonal element. So you will see the tie line tie line connection will be included. And once you have that, you can run the unified power flow with a positive sequence Y bus, stacked Y bus approach. Oh, by the way, well, this will be run in a positive sequence mode because the transmission system is positive sequence, and then you'll be running the positive sequence for the distribution system. At that time, it's balanced because distribution system is completely balanced. Then you'll have. Now, can you include negative sequence? Yes, you can do a negative sequence. So what will you take care of for the unbalanced? You run a negative sequence correction. And that negative sequence correction will go with these corrected tie line Y bus points as a negative sequence. So unbalance is coming in picture with the negative sequence correction. So you have positive sequence first, when you do correction with the help of negative sequence, and then you keep loop in the loop. So you can per unitize integrator on common reverse voltage, compute the active and reactive power when it's between less, then it is yes, then you can get the output. If it is no, compare the equation, solve the equation for voltage iterations around the loop, and then you repeat. So for the distribution network, you will be 3-phase Y bus, you get a stacked Y bus approach, then you get a positive sequence representation like that. So you can do with this approach 3 additional things. Number 1, you can include distribution system as a whole on the unified. Number two, you can run this approach in a positive sequence mode, which means no unbalance on the distribution, reduced. Number three, you can correct the unbalance of the distribution system with the negative sequence and bring it back on the transmission network without having to solve the 3x3 big matrix that we used to have to solve for the distribution system. So I'm just giving you one approach for the unified. I think there are only 2 or 3 people in the world is trying now. This is what we have tried in our lab. There could be some other approaches. I'm not saying that this is the best. I'm just saying that this is the approach that we find it useful and we implemented it. But I think there are a few people have started looking at it very closely. Many are doing decoupled because that's easy to represent and implement it. So 2 different options. You can do decoupled too, or you can do unified. Some advantage we saw in the unified one. So this is how the Y bus will look like. If you are looking at in the form of a positive representation, you will also get the negative representation. You'll get the 0 representation, like I said. So this is positive, negative, 0 sequence. You can actually represent this in the sequence form, and then you can write the sequence balance equation, like 0, negative, positive, and you can actually write the. We can actually only do the positive if you don't care about negative, and if you do the negative, you can do the negative, add to it, or you can do the 0. So if you look at it here, this is a per phase admittance matrix. You translate that into the sequence. So, by the way, you understand that, right? If you want to run in a sequence representation for a distribution network, you have to convert the phase representation of the distribution network to the sequence representation. Otherwise, you cannot run. So the phase to sequence, which is not a big deal. There are converters, phase to sequence converters, but the point here is that you have to take the phase sequence part and then convert into, phase admittance matrix and then convert into sequence admittance. And if you convert that into sequence admittance matrix, you'll be able to you'll get this sequence, phase to sequence submatrices, and that submatrices you have to put that in here. So these are the sub representation of each of those. So now you don't do everything in sequence. Most likely you don't do everything in phase, because transmission network running in phase is a challenge. So you always go the other way around. Okay, the Y bus is ready, right? Once the Y bus is ready, can you run the power flow with one algorithm? Yes, you can run the power flow now with one algorithm. You already see this algorithm before. What is that algorithm? That is a current injection algorithm that we run for the distribution network. Same current injection algorithm, you can run it for the transmission system. Some of the challenges that we faced while we do the unified is basically this, and there are some tricks to avoid the challenge. You see a bunch of zeros here, and this is something to do with any power flow challenge, and this is what we call it as, if you have a bunch of zero, the Jacobian is not invertible. You might have heard this thing in your courses, and we call it in the software call it not possible to get the invert matrix, and mathematicians call this as singularity of a matrix, and electrical engineers call it as these matrices are sparse matrix. All these things basically leads to the same challenge and problem, because you cannot get any inversion. And you see that in here, you will see some sparsity here. See, this zeros are sparse, but the sparsity is okay to solve any inversion. The sparsity should not come on the diagonal elements. That is the biggest challenge on inversion. So if you do this correction matrix, you see this XX there on the correction matrix. If you add that correction matrix, you can actually avoid that. So that is something that we introduced to make the algorithm working. That correction matrix, you have to limit it to some number. If it's very high, that affects the drop. It's a compensation. Yeah, exactly. So that is one challenge. The second problem that we faced was probably scalability. If you run it for 20,000 bus or 30,000 bus, it's going to be challenging. But the idea is to get this type of a framework, and if you get that framework, we get a Jacobian and we can solve. So again, the same story. What is the story? Once you build something, you have to benchmark it. So to benchmark it and test it, and you have to take it and you have to compare that with the unified approach and voltage at each points, and you compare with the voltage error. So this is a spot load at node 14. Basically, you just run one. Oh, so how do you compare it? You have unified now. You comparing it only done separately with the distribution and separately with the transmission with respect to that voltage. That's the only way you can compare. You cannot compare any other way because you don't have another unified to compare, right? So these are some comparisons error for the smaller system. You can actually add, so this is a case we added 4 distribution networks on a node and then tested it out. This is a real IEEE distribution network. It's called IEEE 123 bus system. You can compare that and then connect it with the transmission network, look at the phase error, the average. Oh, you also look at computational time because you don't want to have this take 1 day, 2 days to solve it. So that is something we tested a few test results. Okay, so we talked about the power flow. We extended that to integrated with respect to the power system. We also included DERs in there. So one of the topic which we have to do for the first lecture today is to see whether this type of framework can be used to assess the stability of the electric grid. Okay, because there is a word there on the title called stability. So I'm trying to make sure that I attend each of the pieces there. So what we can do on stability of the electric grid, we can do stability. Everybody know electric grid stability? What are the 3 type of electric grid stability? Huh? Voltage, frequency, and angle. So there are 2 type of stability. One is with respect to the parameter, another is with respect to the time. So parameter with respect to the variable or a parameter, you can call that as voltage has to be, So what is the power quality with respect to electric power system? Little bit different on power electronics, but what is the power quality on electric power system? We call it value quality. Okay. Power electronics, if you move that, then it's more important to look at the shape quality. So it's actually, same deal which we talked about the RMS versus waveform. So the value quality, we talk about what? The value of the voltage that you get could be good, value of the frequency that you get good. We care less about the angle, but that's very important. So angle, so angle is also important, that's parameter. And we look into time. We talk about the quality with respect to larger time, smaller, time, and very small time. So very small time quality, we call it transient quality, and that is assessed by transient stability tools, transient stability analysis. Such tools are called TSA. These TSA tools are actually running, differential equation, but you are also integrating algebraic equation together to form a differential algebraic equation model. We have something called long-term, short-term stability. For long-term, short-term stability, so the angle, you will be seeing that in an electromechanical time frame. Magnetic stability, you will see that in a very small time frame. And the voltage stability, you will see that transient, small, dynamics, slow, everywhere. Voltage has got a wide range of problems on stability. It can be very fast change in the voltage. It can also be very slow change in the voltage. We call it a sag. So this is stability property. Why do you want to know angle stability if you already know the frequency stability? If you already understood the stability for the frequency. Is angle and frequency the same or related? Different. They are different. What's the difference between angle and frequency? Power angle. What's the difference between power angle and frequency? What's the derivative of power angle? Derivative generation system. Yeah, power angle. I'm also talking about power angle of generation system. Power angle of generation system is angle per generation system. So that power angle of generation system, you take a derivative of that power angle. What do you get? There's somebody in between before acceleration. Huh? If you take a derivative angle, you'll get omega. Omega is called angular velocity. You take velocity, then you go to acceleration. You cannot jump to acceleration. So you take the angles, and you get velocity. Okay. Angular velocity. What's the relationship between angular velocity and frequency? What is omega? What's the relation between the angular velocity? Same, proportional. Okay. So now is that angle and frequency related? I made a relation. You said it's not what I mean. Okay. But so then why you want to do angular stability and frequency stability? There is a reason. You're right. You need to do angular stability and project. I'm just trying to clarify some basics. What is why you want to do anchor? It's still the rate of change, right? It's not the same. The rate of change is not the same as an angle. So what's the difference between rate of change and the fundamental quantity? It's different with respect to time frame, right? So it reacts differently with respect to time frame. If it reacts differently with respect to time frame, you have to understand the differences for that. That's the first. Number two is that frequency is a rate of change of angle, and the omega is that frequency not just only dependent on angle, it's also dependent on something else. So depend on something else. It is dependent on something else. Is it frequency dependent on power balance? Power function? So it's not just, of course, angle also dependent on the power, but fundamentally frequency is dependent on the power change or power, angle, right? So that's what you call swing, okay, which is dependent on the power changes, and power change is dependent upon how fast or how slow you can push the power, dependent upon what we call it as inertia. So there is frequency sitting there, which is like we call it global. It's dependent on several different factors. Angle sitting there, we call it local, dependent upon each generator or each bus which is sitting. So you need to study local disturbance and local stability. At the same time, you need to find globally whether the system. That's why we study differently. Now, frequency stability, when you study, you don't study the frequency stability with the help of fundamental power angle curve analysis. You study the frequency stability with the help of load frequency balance or load generation balance. That's all. So the frequency stability, you can call it as a little bit of a not a very fine frame study. It is a coarse frame study with respect to on the larger system. I just fundamentally placed a 10-minute crash on stability. So when you are looking at this kind of study, we can basically study frequency stability, angle stability, and voltage stability. But what is more important to connect distribution network and transmission networks, like Sir was saying, is to understand the voltage profiles of the system. Okay, so this voltage profiles of the system, not just on the head end of the substation. You should be able to look at the voltage profiles on the system on key different points. The substation point, you can also look at the voltage profile on the system at the PV node on the distribution network. You can look at the voltage profile on the system on the transmission one node. You can also look at the voltage profile on the system on the another node, right? This voltage profile understanding is something that we can do directly from the power flow, which is slow moving voltage. Okay, still voltage stability is slow moving voltage. And there is this voltage is a study is performed based on what? Why this voltage changes? This voltage changes based on the power flow, right? going from transmission network to repeater. So there is a classic study method that is already been introduced in the electric power system engineering curriculum to study the voltage with respect to the changes in the active power. And that is something called generating a relationship between the active power and the voltage for every bus, generally known as PV curves. Remember? Have you heard of this term PV curves? Yes. I think it's a stability course we teach, I guess, right? Stability course is PV curves. What does a PV curve meaning? PV. What do you mean by PV? Change in the voltage with respect to the change in the power. Where do you see the PV curve? Well, you see the PV curve for every bus. Can you do the PV curve for the entire system? Yes, you can do the PV curve for the entire system. So if you plot the PV curve for the entire system, will you see the changes in the voltage with respect to the changes in the power? Yes. So can you see that when DER power changes, what happens to the voltage at that point? Yes. So, is this PV curve can be studied for slow moving power with respect to slow moving voltage? Not very fast change in the voltage, not dynamic. Okay, so you have to be careful seeing that PV curve. Once you have the PV curve, what is that difference you can get? You can see what is the point at which the voltage on an electric grid collapse when the power changes. Okay. So conventionally PV curve, when you look at it, we used to draw the PV curve and then we used to study the PV curve. And when you draw the PV curve and study the PV curve, you draw the PV curve and study the PV curve, you plot the P versus V, and then you go and the PV curve looks something like this. I don't know whether you may remember the PV curve. It's like this. I don't know why it is like carbon. I don't want to explain why it is like this because it takes some time to explain. It's basically V and V square and P are the relationship. That's what it is. So when you do a PV curve study, normally we try to increase. You know how you study this? For a specific bus, I wanted to study every time we will put a inverter just for fun purpose. So if you want to study a PV curve on a specific bus, what will you do? This bus has a voltage is equal to 0.98 and load 10 megawatt. PV farm load minus 3. You see I put 10 minus 3. You know what that means, right? So if you have a system like this is a normal condition, right? How do you plot a PV curve? Very easy. This one, you have it. Now you change this. Okay? So conventionally, let's assume this is equal to 0 and this is not there. You change this. Okay? So let's assume that you are here. This is 10 megawatt. When you increase this, voltage start decreasing, which is a norm, and you get to a point, some here, and you will see what point you don't want to go here. You can see what point you will reach before the voltage collapse. Simple. This is a fundamental idea of a PV. So you may ask, okay, is that the only thing which you can do from the PV curve for stability? No. You can also say that, well, I am here. What will be my margin for stability? So how much P I can push on this bus before the voltage on that bus collapses? Is that useful? That's a very useful thing. If I know that for all the buses, that's something which I can understand and how much. Oh, now let us look at the DER. Is that useful when you put the DER? Yes, it is useful for us. Now when you put the DER, which is same old, that's something which I was telling. Everything when you design, you will see that relationship from the old thing, so you can understand. That means if you put the with the BER. What happens to this arrow when you put the BER? So you just start going in this direction. So when the voltage is dropping, when you connect the PV at this point and push power, the voltage will start going in that. You see, now the fun. So now the old PV curve, which you always see only in one side, you have to now start looking the PV curve in both ways, going this way. Oh, is that logically making sense? Yeah, it makes sense. When you connect the photovoltaic on one point, the voltage is rising at that point because you're pushing the power like a generator. You have to balance that voltage. That's your job. Now you can also get an over voltage at this point, right? Now let us look at another scenario. This PV palm output, which is coming with the sunlight like this. Now this thing is going to start wobbling. This is not slow moving, fast moving, but this is what's going to happen when it's fast moving. Just going up and down. Now let's assume that you load the this feeder at this point, and you connect a PV right there. It's going to jump because it's going to go like here. It's not going to stay there because this is what's going to happen. It starts oscillating, and if it starts oscillating, it's very easy. It starts dropping it and collapse. So I'm not making a list here. So one list is a maximum. Second list is margin. Second thing is margin. When PV comes, the first thing what you can do is safe. When you can operate safe, at what point you can operate safe. And the thing is, and then you can also say how much control. Right? You need to control the PV from the reactive power from the inverter. Who is doing all this stuff? Or poor inverter. That's basically the one who is actually handling most of the things, So you have to size. So nobody has done this work and the research part yet. So you could actually do some study on the inverters and how you size the inverter to maintain PV stability for that specific point in wherever the inverter is connected, which is actually not done. It's a power system job, but you also wanted to make sure that how much voltage you are going to maintain with the inverter from the inverter standpoint, the box standpoint, because there is a limit there. You are actually controlling the voltage at that point. You are wanted to maintain that to 1.03, 1.04. You cannot actually maintain beyond that with the help of modulation index and everything. So you have to connect with those. That's basically some other research which we have not done, which we can do later. Is this making sense on that side? Okay. I think we can leave it like this, right? Just screenshot. So with this being said, now I am going to talk a little bit about the stability. So for this part, what we are going to focus is voltage. Okay, PV curve voltage. I will give you a little bit high level overview of the algorithm. The same algorithm that we just discussed, the unified algorithm, you can run this algorithm or the other algorithms in multiple forms. One algorithm that you can use it to run is multi-period power flow. Multi-period power flow is also known as time series power flow. Remember that we discussed it yesterday, time series power flow. So you can run the time series power flow for a transmission integrated system and run the power flow for each phase till the system converge. And once the system converge, you can actually change the power, and then what you can plot is the voltage stability margin. Okay. So this voltage flow, by the way, this I think you should be knowing this or remembering this. So this one, so P and P max, right? Normally people don't represent this in this way. They represent based on the base point. So let's assume the P0 is a base point. Okay. Now the power that you're plotting, you say P, and P divided by P0, you calculate and you call that as a lambda. Okay. So which means P0 is same as the first operating point, the lambda will be 1, and then you increase the lambda. So you call this, when you study this, we call it lambda. Okay. So what we have seen in this graph is a lambda change. Lambda change meaning maximum lambda. So instead of P max, we call it lambda max. But you understood what the relation between P and lambda, which means that you are not actually, you're doing a number and you're a scalar number per unit, a scalar number. So you can see here the beauty. You can study this with zip load, spot zip. You can study spot load with constant P loads. You can study it with distribution system balance. You can study the distribution system unbalanced. All those, what will be the voltage margin? So if you look at distribution system unbalanced with constant P, you see this voltage margin is very low. So now this curve, what you see on that bus when the DER is connected is in the classical stability course. When we teach, this kind of curve will only come when there is a power factor change or capacity, capacitor connected load and things like that. This is called multiple PV. I don't know whether you, and there will be a stability margin line that you plot. And then you call this as the, stability margin. Some of you have taken that course, I guess. So this is how you plot conventionally. You will get a similar type of stability assessment for all unbalanced nature. Oh, this is without connecting DER. This is just the normal. If you connect DER, obviously you can add that as well. Makes sense? So that is what it is.
So we also the power of
Yes. So the margins will be, yes. Each phase also can contribute to different margin. Absolutely. So you can actually put margin for each phase. And then what is the goal here? Goal is to make sure that you take the worst case scenario. So what you do is, why do we do this? If you do all the studies, end of the day you say, hey, this distribution system, I know it's very unbalanced, and that has got some, phases are different, and I cannot load beyond 1, meaning I cannot load beyond the current situation. Don't load beyond V1, because if you don't load, it will collapse. So that is something that can be used, the tool can be used to predict or say with the help of the tool. Otherwise, what happens is you don't know, and you don't know the distribution network how it's connected, and you go and then connect. Actually happened in doing the interconnection for the photovoltaics. I think we will be doing interconnection study here too. So when you are connecting a PV farm to an electric grid, before the connection is done, you have to do what we call it as interconnection studies. Interconnection study is actually a study done to see what will happen if the PV farms are connected in one point, what will happen to the voltage, what will happen to the electric grid, whether you need to add any compensators, so, there are some, I think in India, what I heard from IISc, there are places they are enforcing to add like StatComs, I guess, which is basically to improve the voltage on near the PV farm and some places because of some voltage related problem. So you do interconnection study. This is has to be done, and normally it will be done. I think here also probably somebody is doing that, and also the US people are doing that. But none of the interconnection study do any of these kind of study, which I think is important, because you will It's dangerous, if you look at it that way and if you connect the PV farm. Because location you cannot change. So that is decided by policymakers, government, some other people. It's nothing to do with technical people. They don't do anything. It's just location. The only thing what you can do is you can strengthen. Oh, another question. Can you make this PV curve robust? Can you load 4 up to 4? Can you do that without doing anything? Yeah, if you can improve this voltage shape, go like this, then I think you have margin. How do you improve that voltage shape better? Dynamic compensator. You should have some kind of a compensation, voltage compensation. Voltage compensators are one way to do this or take care of. But do that voltage compensation, you need to know what is the size, where do you connect it, how do you compensate, how much is this. 4 is a number that you get. Well, I'm happy. I got 4, then I can find when 4 happens, what is the voltage, and then I can do all that. But there's a tool that is required for that, right? So there's one example of stability tool that you can, one example of power flow tool that you can use it for stability study or, voltage stability margin assessment. So, I see. Yeah, so you can actually plot this. So this is basically the PV curve, upper part. It's like lower part plotting is not you need to do some. So if you see plot like this, you can see this is P with the transmission system with the spot load. So if you run a transmission system without a distribution system connected, this is the margin that you see. So the T with the equivalent distribution system, that's the margin. Positive sequence P, that's the margin. 3-phase P and D, that's the margin. So you see the whole thing, and you know the lambda, right? So the whole thing is going from 4 to almost 1. And in some cases, with this is a constant power load. With the zip load, even it goes all the way to 2. Oh, zip load, we are saying that is better now than the constant PQ load, which is, I think, is good because you are reducing the power of the load based on the voltage. So all these trend lines you can get with the help of our simple power flow. Lot of effort to put it to run that power flow, but it is not even if it's time consuming, it's not going to break anything. I mean, you just run the power flow, like 3 days after that you get it, it's okay. At least you will get these numbers now. Then you can. Now this continuation. By the way, I have to say something about this. So this PV curve, generating the PV curve with the help of power flow is done by several different ways. One method to generate this PV curve is known as continuation power flow. I don't know whether you have heard. I think some of you might have already heard about those things. But continuation power flow meaning you've done the power flow continuously. Okay. So you may call it as, if you run the power flow continuously, you call that as a multi series time power flow, right? Continuation power flow is not that. Continuation power flow is a little trickier. You run the power flow multiple times, you can reach here. But to reach here, you will need to do some tricks. Okay, that is done by continuation power flow. So I'm not going to go with the continuation power flow. So you see this power curves, PV curves, plotted. This is the PV curve without DER and with the DER. What happens when the DER comes in place? If DER is pushing the power, PV curve is kind of extending because DER is getting more power onto that because it's going to the light load condition. So the PV, so you can see that. What happens to if there is a transformer taps? Transformer, you remember LTC, OLTC, that is on this distribution. When the transformer tapped with the fixed tap, no tap, this is a PV curve. When it taps, PV curve is getting it. So now you can say, hey, I am regulating the voltage of transformer. What will be my PV curve? I can assess that. So that is actually on the head end. So you just go with the one voltage at that point and see what is the PV curve there at that point. And you can actually do. So we proposed, and there is a paper in here. I don't know. I've not put the reference there, which you can read. So that's basically the first Any questions?
Kind of. Suppose we are interacting the entire distribution system at one node on the campus. It's a kind of more dynamic load kind of.
Suppose on the same bus, we will remove the distribution system and we have to add some dynamic load kind of thing. Because in the distribution system itself, as you told, R by X ratio, that will be very challenging task to manage. So, in terms of actually market, I would like to ask here that like demand response analysis, suppose we are doing and we are managing the things, then it will be very disturbing for the transmission systems. So at the same time, because distribution system will always disturb the transmission system. So under this scenario, whether it will be beneficial to go for combined power flow or separate power flow, and then we can.
Very good question. The answer is kind of yes and no. Depends on what exactly you want to study as far as markets are concerned. So let's assume that you are studying on electricity market. You are studying the active power transfer. So when you do study the active power, you will be studying at this point the power that is going, and let's say this is a transmission network. You are looking at the exchange point in here, how much power drawn at this point, how much power drawn by here affects the power output from the transmission side. So if you are going to look at that, this so this is basically, I'm talking about changing topic here. I'm talking a little bit about electricity market, how the electricity market runs. So in the electricity market world, how it runs is, it actually look at the power that is being scheduled and power that is being consumed. Now the power that is scheduled is not the same as power consumed. You will have some challenge. You will have to pay more money. Okay, so that money, whatever you pay, whether it is extra generation or whether it is extra generation adjustments, so you don't have to generate probably extra, but you have to adjust the generation. So for example, suppose you have, this is a cell and this is the load, right? Here you don't need to generate extra, but you need to adjust this. You see, somehow you need to adjust this. So how do you adjust that? Well, you adjust that by putting some other device or ramping up or changing something on the generation. That is basically your cost, extra cost. But instead, let's assume that in here it goes like this and then it goes like this. At this point, you need to change the generation to another generation. So this is the market problem. Okay. So you do markets in different time scale. Everybody probably know. One is called the market ahead of time, long term planning. Second is market a day ahead. It's called day ahead markets. Then you have the market for hour, every hourly market. Then you have what is market, we call it the real time, where you are going to, at this point, how much I have to incur the cost, so I need to adjust it. So depending upon the real time changes in a day, for example, every hour or something, you may give you a signal to the load and ask the load that, hey, if you can, please stop consuming power, if it's a very bad scenario. Okay. So the demand response, basically what it means is, you are going to give a signal to the load and say that you either need to shut down the load or shift the load. Okay, this is done normally in what we call it's a TOU. I don't know, it's maybe same name here. Time of use tariff. Time of use is basically Every time you use the electricity, you pay money extra according to that. Not a flat rate, So there will be a flat rate, but there will be extra money that is going to happen. But anyway, so the question is, in this context, how do you model the distribution network and then connect it to the transmission system? If you to model a distribution network and working as a disturbance, you can model this distribution network as a slow changing PQ load and then study. Okay. But if you are running as a dynamic case, basically for the stability, that's a different thing. That actually has to add based on the market. So market study is the operation. So that is why it is a little different. Basically, Dr. Tiwari okay, so what we will do, we have 30 minutes, I guess, right? We will switch gears now. If no other questions, we will move to the little bit of another topic. And that topic is, now we started looking into controlling IBRs, okay, managing controlling IBRs. So let me talk about the context. So now this is your so if you look at an electric distribution network, this is your load generation, this is your IBR, right? So now when you look at it, you will see that the I'm just making a shape here. This is with respect to time. This is the power for the load plus DER. Okay. So what we have done so far, we have looked at how much the power balance happens, what will be the voltage, how the voltage can be controlled or balanced. I mean, how the voltage can be seen with the help of power flow, right? And then how the power flow changes, right? We have not touched so far. How can you control the DERs? So to control the DER, you have to give some reference, right? That reference power to control the DER will come from the power flow and then next. Yeah, controlling is difficult. Yes, it is difficult. How do you control? That's what we're going to talk about. So, so basically, if you can control, let's assume that you can control. If you can control, then obviously you can actually adjust this shape. And if you can adjust this shape, you can probably get a better match with respect to stability now. Okay. So now let us say that you have a DER at one location and you have several of these DERs. And this DER is doing this. This DER is doing this. This DER is doing this. Okay. If you add all these together, you will probably get a shape like this. Now let's assume that this DER 1, 2, 3, this is a PV farm. Okay. It is a PV farm. Most of the output from the PV farm, you will say that you cannot control because you have to put maximum power coming from the PV and then you take out. So those PV farms, output P cannot be controlled in general. because you take the maximum power from it. But for those PV farms, if you have an inverter connected, you can control the Q of the inverter. Good. So that Q of the inverter you can control. So first thing which we can say, if we have any intermittent sources connected, you have some available Q that you can control from that intermittent source connected at the inverter. So you can give a set point from the optimal power flow or power flow to that inverter, and then you can track the set point. Good. That's basically Q for all the inverters, right? How do you control P? So you control P, only way you can control P is by making this DER dispatchable. Right? Now this is not dispatchable. Oh, you understand the difference between dispatchable and non-dispatchable? I think we discussed this yesterday and day before. I think might have brain out. Dispatchable generators are synchronous generators, for example. What is a property of a dispatchable generators? If you say 5 megawatt, if you ask for it, it will give you 5 megawatt. Not maybe now, within 3 seconds it gives. 3 seconds it gives through governor. Talk about the storage. This is a dispatchable. So here if I want 5 megawatt, this guy cannot give 5 megawatt, says there is no sunlight. So how do you make that inverter or in the PV farm dispatchable? The only way you can make it dispatchable by energy storage. That's the only way you make the PV farm dispatchable. Right? Now, where do you connect this energy storage? It's up to you. Whether you can connect the energy storage along with the PV farm and then convert the DC to AC. Right? Such PV farms with the storage are generally at the, we call it behind the meter, meaning not seen by the utility. It's in the rooftop or some places you always have some battery or the PV connected to the battery, and then you have some DC bus. I'm not going to draw the picture, but you can see the picture, right? PV, battery connected to DC, then to inverter, then to AC. One architecture. What's the second architecture? PV, multiple PV in one like neighborhood, one battery, again connected to DC bus, and one inverter. What's the third architecture? Multiple PV, inverter, one battery, inverter, again connected to the. What's the fourth architecture? Well, multiple PV in a long electric grid. Utility will go and say, hey, lot of PVs here, it's all changing. I'm going to put a battery connected to the inverter and to the system. I'm not looking at the individual PV control. The entire area, I'll put the battery and I'll control the battery. Right? So, we divide the asset, PV farms and battery, into two. One is controllable asset, another one is non-controllable asset. Non-controllable asset, for the active power, it pushes active power, whatever you want. Controllable asset, which is done in the form of, for example, energy storage. Now, this controllable asset is money. You need to find when to, how much to size, where to put it, how many to put it. If you have a tool to understand what are the problems, how much PV comes, how much you need to put, then you can design what will be the size of the battery. So normally there is a question, what's the size of the battery, where you put, how many you put. 33%, 40, 35% is the rule of thumb, that you put PV farm and then you have a 33% battery with respect to the performing capacity, which is including capacity factor of the PV farm, when that battery is moving. So this is how you manage the PVRs. Is that story, you understand, right? So what we are going to do now, we are going to discuss some methods coming from the top level, meaning on the distribution network level, how you develop a tool to understand what are the changes in the PVs if you have a battery connected in different locations, what it can do, fictitious battery connect models, which you have battery connect, what it can do, and then you can analyze based on that where to connect the battery and what to connect the battery. And everything is done through battery energy. Oh, I say keep saying battery. It can be any energy storage. It doesn't really mean that it has to be battery. It has to you have to store the energy. That's the idea. Good. With that premise, and of course it's intermittent, and it may be variable. Some other variable factors can also. So with that being said, I'm going to show you some methods that we have developed and implemented for controlling the DERs. Oh, when we call it controlling the DERs, you assume that controlling the batteries. DERs are, so anyway, distributed energies or resources. Distributed energy resources are distributed. It doesn't really need to be PV. It is basically, yes, of course, you cannot do anything to PV. So if you want to control, what are the challenges? Challenges is the intermittent nature of DER, which causes uneven voltage profile. Penetration level can increase, the voltage profile can be optimally balanced. So the goal is to balance the voltage profile and at the same time supply how much power you need to supply from the battery to balance the power output, power schedule. So what you need is a reactive power management. You will also need active power management. Okay. So first I will talk about reactive power management and how you do that. So there are two ways you control a DER unit. One way you control is local, or we call it also decentralized. Another way you control is coordinated or centralized control. So there are two different ways you control. I'm going to talk about both of them, like two examples rather, and how you can adjust. And the good news or bad news is that you will need to have, if it is locally controlled, you don't need a communication link. And if it is globally controlled or coming from the substation, you need a communication link. And locally controlled has a challenge that you cannot get the global signal. So you will not be able to manage, for example, frequency and voltage. There are some pros and cons. So how do you do a coordinated control? So is one approach that you can do for a coordinated control is linking optimization with control on a central location. Okay. Have you done optimization? Yes, we did optimization. And optimization architecture linking with control is generally comes under the classification of optimal control. Okay. So what do you do in optimal control? You are going to minimize an objective function and design a controller output. Okay. When you do a controller output, oh, by the way, I also need to talk a little bit on different level. So this control, if you are controlling a DER, that's generally called device level control. On the device, the DER control happens. Okay? If you control the DER or group of DER, we call it secondary level control, where you send a signal to the group of DER. If you control the DERs in entire substation and send a signal from the substation point, we call it tertiary level control, where you are going to send a signal from the substation point. If you are running an optimal power flow or a power flow, you are going to do either tertiary control or secondary control. You don't do device level control, which means that signal of the power comes to the substation, say, hey, I need this signal. That signal goes to the group of DER and say, hey, I need this from you, this from you, this from you. And then this go to each DER and say, hey, I need your contribution. So you divide them into that's how you send a signal. So when we are talking here, we are talking about sending the signal for individual DER for reactive power compensation. That's the first thing. So you take in a transfer function form an objective function, and you minimize the objective function with the help of a transfer function which relates voltage and reactive power. So this reactive power, so in this case what we are considering is 3 inverters. large inverters where you can control reactive power. Again, we are putting the active power topic a little bit later. We'll talk about that. So reactive power and voltage can be balanced with the help of this equation. So this is objective function and this is a constraint. So this objective function is, you can see this objective function, you can represent that in the linearized form. This constraint is, what type of constraint is this? What type of constraint is this? We learned about constraint yesterday. What type of constraint is this? This equal sign. So what type of constraint is that? Now look at equations, but you equality, yeah, it's equality constraint. You see what happens if this is not equal sign? It is non-equal sign. It's an equality constraint. So equality constraint and a objective function. Basically, the equality constraint says that this whole error, which we call it as a Lagrangian error, you wanted to make it equal to 0. So you can take a target node reference. You can look at the voltage on that point, change in the voltage, run through this algorithm, get the controller set point going out for each DER. Okay. How many DERs we are considering? 3 DERs we are considering. What are we controlling? Voltage. Are we sending reactive power from the DER? No. We are changing the reactive power from the, who changes the reactive power? Inverter changes the reactive power from the DER. So we are actually sending inverter set points to the smart inverter basically. How the inverter changes the power inside the inverter, that's the local control or the device level control. We are not talking about that. We are still on that level, not on the, I will tell you probably in the advanced topic on Friday or something, how the inverter control really happens, inside the inverter if there is an interest. I don't know whether you have interest there. That's a different thing. So just wanted to keep at that level. So here is a distribution network. We are actually showing DERs in here and 3 DERs. And this is the node of interest. You see, this node voltage is very bad. You want to actually have these 3 DER control this node voltage. So you may ask the question, if this node voltage is there, anybody else can control other than this DER? Well, you see this thing here that can control this voltage. What is this? Voltage regulator sitting there, which is going there. Now, do you remember voltage regulator? We talked about that. Voltage regulator can control. So that is called a legacy controller. This is DER control. So this is what we are going to do. So we are going to see a drop in the voltage, and you wanted to see that the voltage can be controlled back to 1 per unit. So you can see that this voltage is lifted back to 1 per unit because of the reactive power coming from the inverter. So you can actually use this reactive power from the inverter to control the voltage node. Oh, can you use these 3 inverter to control the voltage here? Maybe not possible because that's too far to control. You may need a local, DER to control that voltage. Good. That's one study of reactive power. Tomorrow we have a session, or maybe even today afternoon, or either tomorrow, I think we have a session where I will show you how this reactive power can be coordinated with this regulator. So if this reactive power is pushed to control the voltage, this regulator also will be seeing that, right? What's the regulator going to do? Regulator is look at the voltage on the load side and control the voltage on the. So regulator is actually looking at this point. So if this 67 is pushing reactive power here, this regulator will be looking at that, right? So which means it affects the regulator operation. So how do you coordinate with them? We'll talk about that. So there is a little bit of challenge there. It's not that easy that you push reactive power and voltage is controlled. There should be some coordination challenge there. That I think we will talk about that. But for now, to answer our fundamental question, can you send a signal to control the reactive power? The answer is yes, we can send the signal. Now, can the signal sending done from the power flow? No, you need a controller. And that's what we are discussing. So where does the power flow comes in here? Power flow comes in here by keeping this reference voltage. It will not do anything how that is managing the reference voltage. You see? So power flow will say, I run the power flow, I say this is the voltage I have currently, right? I need to have this point there. So power flow will be able to tell you what we can do, or optimal power flow will be able to tell you what we can do, how much voltage you need to maintain, and then the controller works. You see the difference? What comes first and why, how it comes. And to whom. So all those things are, I think probably you'll get some clarity now what we need to do. This one is one architecture we developed and implemented. I'm not saying that is the best architecture. It's one method that we are doing it. That's important, but you can do similar methods like that too. Good? Makes sense so far? Okay. Now we will do is I think our friend is not here today. Can you do active power control? That's something which we wanted to talk about. So in the active power control, I am trying to show you something, active power and reactive power for the group of DERs. So now we are doing one DER, right? That before. You want to see in one group and see whether you can make a load generation balance of that group. Fictitious. Okay? It's difficult to do it through mathematics. So you can use at that point some things like machine learning. Okay, so that's why if somebody is interested in using, I don't want to use the word parametric optimization like a genetic algorithm or something. If somebody is interested in using any machine learning methods, you can use a machine learning method to find out the groups. So here we are using a machine learning method to find out if you have a distribution network, how do you make groups? Okay. What is the property of the group? The property of this group is that this group will be self-sufficient with having power in that group. So for example, we have 5 of us. There's a loads connected and we are generators. We want to make sure that within 5 of us, we have enough generation and the load when photovoltaics are connected to take care of the load in our group. So we are self-reliant, self-sufficient. You don't have to depend on another group. We are fictitiously calculating that, meaning we are understanding with the existing resources what will be the power balance, okay, for the PV farm changing. So you have several of us there in the distribution network, PV farms are changing. We are finding how we can make a group such that there is no power exchange between two groups. That's a goal. So if we can achieve that, that means we are self-sufficient, right? So what is this grouping? The grouping is exchange between points and then cut it, then I'm good. Okay. This can be done through, so this is a project that we have implemented in the field. So we tested it in the lab and tested it in the field. And this is an example of the group. So you see these groups making different colors, meaning they are having this different color. These are fictitious, and then we implement it in the field, how it's been done. So you can do that using clustering. Okay? I don't know if you heard this. When we started our day in the morning, 5 o'clock, you have rain. Then we have a heavy rain. Then we started our session a little late. Now we have disturbance here. Door is open. I normally don't talk with doors open, which is a little bit distracting. So if you keep talking and I'm just in a flow and formulating my thought, making sure that you understand, suddenly solve this, and then I'm just. We should close it, I guess. Nobody comes now, I guess, yet. We'll have 10 minutes and then probably we are done. Is that good? Yeah. For so one group falling short of power can happen. So you will be able to use the controllable asset, for example, battery energy storage, to supply that power in the same group. And so you may ask the question, well, do you need a controllable asset in every group? You may not. Suppose you have controllable asset for 5 groups, then that controllable asset in that grouping of all the 5 groups can send signal to each group and then send the power. If you do that, then there is a power flow. There will be some power flowing through that. Yeah. So you can do separate, you can do together, you can do depending upon whatever level of flexibility you may have for your battery. So let's assume that you have battery in every group, you can do it. So battery in 4 groups together, you can do it. Suppose you have only one battery for the entire district, you can do that too. And what is the trade-off? What's the challenge? The challenge is, if you have battery in every group, then your losses are less and controllability is more. Battery size is low. You can actually, flexibility is more. So this is one good news. The bad news is that your cost is high because you have batteries in every group. So the tool, what is giving you is gives you flexibility on whatever you wanted to do with respect to your asset. Depending upon whatever you have in your utility, you can change. And it also gives you flexibility. What happens if you scale the PV farm? If you have more PV farm comes in future, what will happen? So the groups will tell you whether you need this balance is more, and things like that. So you can be flexible. You can do either way, depending upon what level of controllability you have. So the utility, when we implemented, utility said that let's start from small, which means let's say that I have only 3 battery and I control only 3 battery. All the PV farms in that feeder, let it do whatever it wants, and I control 3. We control 3 for each area. The group that you are making, you do for 5 groups together, and that gives a set point for the 5 group. You divide that into each group and then send the signal for each group. The only thing is that you should make sure that it's tracked, whatever set point it is. And we did that because they want to make it simple for implementation. Make sense so far? So you get to, I'm just doing, so you can actually run the power flow and find out the sensitivity of voltage with respect to the reactive power. You can look at the Q S square minus P square from the inverter, and you can find out whatever the reactive power should send from each inverter for that group. So that's the reactive power, voltage. You can also do the active power. So now I will tell you groups. So this is actually the cluster. Groups are clusters. So you see 1, 2, 3, 4, 5. There are 5 clusters. You see the different colors, right? 5. And then you can see the BESS, which means battery energy storage. We are assuming for each group there is 1 or 2 battery energy storage. Okay? So you have looking at control of the battery energy storage. Now no reactive power available at the DERs to support the voltage. Now what you do is that you started getting reactive power available at cluster number 3 and 9, so 2 locations. Then you see cluster 2 merges with cluster 3 and cluster 5 expands its boundary. Why we do that? Because we have sufficient reactive power. So another case is reactive power available on 3 locations. Then you see forms a new cluster 6 from cluster 5. So you actually have a group, another group. So what it tells, summary is that you can change. So what we do is we run a power flow. Remember that in the utility you run the power flow every 30 minutes. While you run the power flow, depending upon the time, you can also form the cluster. Every 10 minutes, every 20 minutes, we can see what will be the cluster. That is it. So if you have a cluster, you can actually do cluster control. So basically this is optimization algorithm to do the cluster control to give set points to each DER. So this DER set points are, we can actually have batteries. Batteries are working on the set points in this case. We're talking about the battery for every place. You can actually reduce number of batteries. You can look at the state of charge of that DER and you can balance that state of charge. So if you do like that, there is a math algorithm associated with that. You can actually look at the change in the voltage available Q for DERs, and we can also look at the how much you can supply from the DER. So this is a data. So you get the signal from the field through a TCP channel, and you write a Python routine on a proposed control architecture, running the power flow, developing cluster, and sending the set point back to the field. Through the TCP, it goes to the field, and from the field, it actually works on the devices implemented on the. That's basically the centralized algorithm approach. So here is changing the cluster. You are improving the. So we test this. What we call it net load. Everybody, we know net load, right? What is net load? This means generation minus that. So in each area, if there is a flat line I see, that means I know that I am not borrowing power from you. I'm self-sufficient. And if there is a spikes I see, which means I am borrowing. So we call that as a net load. So we want to have a flat line at 0. Oh, what happens if we get a flat line at 100? Which means we are getting power from the utility 100, but it's a flat line. Still it's good because utility don't want to say, oh, my power is changing all the time. It's a constant power coming from the utility. So it's great. So the goal is basically first flat line at 0 or flat line at any other number. So you see that we want to maintain it like that. Now voltage. Voltage, you can actually maintain the voltage with whatever the voltage set point. Ideally, you need a flat line, but if there is a variation, it has to be within the limit. So here is a voltage profile for every node in the distribution network for a period of 2000 seconds. This is the changing with the photovoltaic. This is the voltage with control on the inverters, assuming for the control on the node. And this is the variation in the voltage node with the control and without control. So you can see how much you can maintain the voltage within the limits. The next one is sharing the power. So what we did, then we said that, okay, can we actually share the power with a global objective? So for example, the utility says that I need a power to the utility. Have you heard of grid auxiliary services? No, auxiliary services? Yes, heard of it. Have you heard of frequency response, frequency regulation? Yes. Frequency regulation is maintain the frequency constant, right? So frequency regulation normally happens, get messed up if you have a varying power, right, from the generation or the load for that matter. So to regulate the frequency, utility either conventionally do is load frequency control and the AGC and the governor, the conventional center. When the DER goes in place, the generation varies, not the load. So if the generation varies, you need somebody else to maintain that frequency regulation, which is basically DER. So utility asks, for example, battery or some devices to give extra power to regulate the frequency. So in some places or in many places, battery value is only the frequency regulation, especially in the US, because other people says that battery doesn't have any value because I don't think battery is needed for the PV farm. So frequency regulation, when it happens, it actually can go all the way to distribution network in the form of power. So I can say to the group, I need this power. So not flat 100 kW or 200 kW, I changing power with respect to time. And that you can ask to maintain the frequency. This is called ancillary service supported by devices in the field. So if you have a set point like that, how do you distribute? So here is an example of that, where we can see a set point coming. We call it area reference. Every time, it's a 12 o'clock in the afternoon, 15 minutes later, 1 o'clock. So this is a set point. And you are asked to deliver the power from the PV battery combination to honor the set point. So this is the PV output without honoring the set point, that blue. So the goal is now using cluster, you are making care of honoring the set point. And at the same time, error, reducing the error to 0. And now you can see who is contributing to the set point. Cluster 1 is contributing like this. Cluster 2 is not contributing. Maybe at that time photovoltaics on the cluster 2 is not varying, intermittent. Cluster 3 is, so now if there is no cluster battery, well, it doesn't matter. You can actually use the entire battery together to support for the cluster. Yep. If you have a battery on each cluster, you will be able to see how much cluster is self-sufficient or not. Groups. And then this is a feeder head power flow. So feeder head power flow, if area reference is constant, then you don't need to get the power from the substations or beyond that. What else? So that is basically the summary in here, and you can also adjust based on the capacity of the battery running out of juice, which means the battery is low. You can adjust the power based on that battery. Okay. So I think we are almost running out of time. I wanted to see if there is anything specific I want to talk about. So you can actually run this for multiple PV farms located at different nodes. So this is assuming that there is a cloud passing and the distribution network, but this PV farm see the cloud, the other PV farm don't see the cloud. So you will see this intermittency is changing depending upon several PV farms. So you can put that this is the load. So you'll get the net load. Each place is different. So you can actually see what will be the cluster in one time and cluster at another time. So, it's moving with respect to time. And then you can see what will be the power contribution. So you see right here, you see this is the reference. And if you look at here, it's not tracking the reference. You know why? Because there is a high intermittent nature and there is no enough battery capacity. So it's not that you should do everything perfect. You can also see what is the problem, and then you can design solution, meaning you need to increase the capacity of the battery, whether you need to readjust. You could do that. think probably that's, and then this is a voltage profile associated with this. So what we have learned today is two parts. One part is we learned how you can extend the power flow to use that power flow to maintain voltage stability or voltage balance. Then we started from the power flow. So power flow, optimal power flow, and time series power flow is what we have covered in last few lectures, and using that for stability as an example. Then we started moving that from that to higher level control, we call it tertiary level control or secondary level control. How you can use that set point from the power flow to derive control objectives for an electric distribution system, not the individual inverter as a high level, and then how you can from there give set points to a group of BERs, controllable assets with respect to the battery. So that's where we are. Tomorrow when we come back, what we will do is we will use that same framework with the DER, and I will show you how you can coordinate with the other device in the distribution network with control. And then we will go into how you can control individual inverters for voltage frequency balance. And then we will do how to implement it in software. We will try to use a real-time simulator example of how to implement it in software. I think there is a homework assignment which is, I think, due today, so you will be able to deliver that. I will probably give you one more problem to solve using MATLAB or something for tomorrow. So that's basically our plan for tomorrow. In between, if you are in this and thinking about it, and if you want to bring up with any specific area that you want me to attend or talk about, bring that questions to organizers, and we can talk about that tomorrow. So from now onwards, we will be obviously continuing control, advanced topic, real-time implementation. We will also want you to feel it and then ask any questions, anything specific that you wanted to mention. So that's basically what I'm thinking with respect to summary. So yeah, any questions on this so far? Any questions on what we have talked this morning? Very easily. So now, well, it's a very good point. So when we did this, we talked about batteries, right? And several battery combinations. And then we say that the energy storage is used and then power balance happens. The same proposition, you can say that, hey, the battery is not there. You have two pump storage or two, hydro plant. How do you deliver that power? You actually have to model and you have to see the ramp rate of that and then see what will affect and where it can be contributed. That's one thing. You can also implement and see suppose you have a inertia dependent source like a flywheel or something connected to it. What will happen to the power swings or power changes and then frequency? So we can plot the frequency on this system also. So yes, it can be extended to other type of energy storage, frequency balancing or load balancing solutions. You can also implement to see what happens. You can also implement on the same model to see what happens if you add a reactive power compensator like a StatCom or some other devices. So the architecture wise, I'm very because this has been vetted by several people. So architecture wise, I think it is it's very flexible. The algorithms or the controllers or the devices, you can use the same model and then build your own framework and out of that. But this is kind of a feasible model that we can. Yes. Any other comments? Any other questions? Okay, so we'll disperse now and we will, I think it's a session in the afternoon, but we'll come back again for the lecture session tomorrow. That's right.
Thank you, sir, for your insights on modeling of IBRs in distribution system as well as transmission systems. So thank you to all for listening, the sir. Actually, one thing that I would like to say here, that assignment was given to you yesterday. So you have to submit it in a reply email. Okay, whatever the email you have received. Okay, so you have to supply your response in that email. Okay. So today is the last day. You have to just complete it and submit it. So again we will meet at 2:30 sharp to proceed with the another session of Professor Asheesh Kumar Singh sir. And tomorrow again we will continue with Professor Sukumar Kamalasadan sir as per the schedule. So thank you all. Thank you very much. You can have a cup of tea outside the hall and then you can go for bed. Thank you.
Hello, hello.
M.Tech in Control System from REC Kurukshetra in 1994 and his doctorate from IIT Roorkee in 2007. Since 1995, he has been a faculty member at MNNIT Allahabad. His research interests include power quality, e-mobility, smart metering, AI application in power system, energy management, and smart grid. He has published more than 140 research publications in peer-reviewed international journal and conferences, and co-authored of 3 books and 20 book chapters. He has also organized several short-term faculty development programs focusing on various power system issues. He has delivered 60 lectures at various national and international forums. He has supervised 15 doctoral and 64 master theses. Also, he has procured research funding of over Indian rupee of 2 crore since in the year of 2015 from various international and national funding agencies. Currently, he is a senior member of IEEE, a life member of the Indian Society of Technical Education, a life member of the System Society of India, and a fellow of the Institution of Engineers. Professor Singh is also a recipient of the Outstanding Energy Award Engineer Award in the year of 2020 of IEEE PES UP section chapter for his outstanding contribution to the power engineering profession. We are truly privileged to have presence and expertise with us. Please, sir. Thanks.
हाँ ऑन करिए वो चलिए सर थैंक यू वेरी मच महिमा for this introduction. So I have been given this assignment to deliver a lecture on this integrated electrical grids with IBRs, right? So we will talk about what are IBRs, where they are in our grid, how they are affecting our grid, what changes they are bringing to our grid, right? I think yesterday, day before yesterday, we are aware with the IBR, what is it and how they are functioning in the power system. That has been covered by the earlier speakers. So, what are IBRs, right? So, you can find that there are 2 different types of sources in the power system. One is synchronous and second is non-synchronous, right? So, these IBRs are those which are non-synchronous. Synchronous means we call them synchronous machine or synchronous motors or synchronous generators like this. Are you aware with this or not? Right? But this new generation resources which are being used in the quest of this addition of renewable energy where we are trying to decarbonize the grid, right? So we all know that nowadays our grid is going through a transformation under the impact of 3 Ds, right? What are those 3 Ds? First is decentralization. Means we are earlier, what happened in earlier days when this power system started, we put all these generating stations at a central place where the generating, either the generating resources were available. What were the generating resources? Resources for the generating stations were either water or coal, etc., etc. Right? So either they were close to the generating stations were close to the load or closer to the availability of raw material for the generation. Clear? So that was the era when we started doing the things in a centralized manner. Clear? And
Another point which went into the support of this in this centralization, when we tried to do it as a centralized way, that the cost of per unit electricity was decreasing when we are making it in a larger way. So that was the time. You will not, I hope you must have seen the power plant, thermal power plants or something. Have you visited or not? How many of you have not visited thermal power plants? Not visited. Have you visited any power plant? Thermal, hydro or hydro? Which plant?
Which means
What was the capacity? No idea. So that was making electricity using flowing water, right? So there must be a turbine, and that turbine, under the impact of flowing water, when water flows into it, that converts it into this energy. Which energy? Potential energy is converted into electrical energy, right? So this electricity generation, as we say now, so this all is an energy conversion basically. Do you agree with it or not? So we all know that energy transformation takes place. Form of energy changes, right? So let me give you one assignment. You just note it down in your copy, right? In how many ways the energy is being converted in thermal power plants, where you are making electricity from coal, means the energy is stored in coal, and how this stored energy in coal is converted into electricity, that is another form of energy or electrical energy. Agreed or not? So there will be some n number of stages between these two, means in this transformation process. Agreed or not? Right? Similarly, you can also consider this hydropower plant, how this electricity is, or how this energy is transforming into electrical energy in case of hydropower plant and nuclear power plant, right? Then you can tell me in that question, answer of that question, how I am talking about these three I have told you, right? Among these three, which two are closer in functioning or more similar in functioning? Clear? So these are three questions for you, right? This answer you shall think on it. If you do not want to submit, no issues. You must be aware with the answer. The question is clear or not? Right? Okay. So, so this was the story when this came into the centralized generation, right? But when this era of renewable energy came, or we started talking about this net zero impact, or we started talking about the pollution or climate change, etc., etc. So there were n number of resolutions were made at the global level, right? That is not the discussion topic today, but I'm just touching it today. Clear? So what happened? Then we started thinking about generating electricity from the renewable energy resources, right? Then second term came, we will go for this decentralization of generation. Means we will generate electricity closer to the point of consumption, right? So what we started doing some this small electricity generation at this hydro plant or thermal plant, something like that. But you must be aware that you will not find any thermal power plant in the range of 100 kilowatt or 200 kilowatt. Agreed or not? But there were earlier. ठीक है, आज से 30 साल पहले, 33 decades or 4 decades before, this Panki thermal power plant, where I did my training during my this BTech days after second year, that was having 3 units of 100 into 3, 100 megawatt into 3, right? And right now you will not find any unit less than 500 megawatt or something like that. Is it or not? So this is the transformation which has taken place, where the centralization of electricity means larger electricity generation at a single generating station took place, right? And what we are doing now, we are talking about opposite, entirely opposite to that, where we are trying to generate electricity closer to the point of consumption using this solar panels at our rooftop, using these wind turbines in our closer vicinity, or simply these small hydropower plant. You will not believe the government has given license for several hydropower plant which are generating in the tune of 1 megawatt to 5 megawatt electricity in the Uttarakhand, right? And another new point is that even NTPC, which is the National Thermal Power Corporation, they are bidding for it, right? So there is no classification now that this particular company cannot go for the another mode of generation. You will find that near Unchahar, when you are crossing this Lucknow road, you will find that there is a board and NTPC is owning some solar power plant of some 10 megawatt. It is an old story. They maybe updated them, right? And there are solar power plant right now which are generating electricity in the tune of megawatts, right? We call them solar park, right? Another question is for you, what is the largest solar power plant in India? Answer is not required here, right? You must be aware with this, right? It will increase your knowledge. Number 2, within this 200 kilometers of Allahabad or 300 kilometers of Allahabad, maybe 250, are there any such solar power plants? Right? Some 2 years back or 3 years back, our Prime Minister inaugurated similar plant in some very close vicinity in that radius of distance which I am telling you, right? So you must be aware with those things. What is renewable energy generation, right? And wherever this renewable energy generation is taking place, they are coming under this category of inverter-based resources. Agreed or not? Right? Because this generation is taking place in one form of electricity, and for consumption, you have to process it in some other form of energy, electricity. So in this process, during this transformation process, in the last stage of generation, this comes or make it useful for the users of the consumers, right? This is IBRs are very much present in the system. Clear? Second, what was earlier story? Earlier story was, in earlier days, there was a power system book. Used to be, every power system book was having the questions like this. This is the load curve. If the load is following or load is increasing in both ways, how many number of generators you will have to start, or how many number of generators will be required, and extra generators you will have to make off, right? So that was the period when the centralized power generation stations were there. We used to call this phenomena load following generation, right? Load badhega, generation will increase, load will decrease, generation will decrease, right? Now, the scenario is different. Today's scenario, I am having a rooftop solar plant, right? I may or I may not have electricity connection in my house. My work will go on. If I am using battery energy storage, why this battery energy storage is used, right? So with these renewable energy resources, it is considered that they are technically dependent upon the climatic conditions. Wind is more, wind generation will be more. Solar radiance is more, right? Solar generation will be more. But there may be time when the scenarios may be vice versa, right? And there may be conditions when your requirement of electricity is more, right? But your generation is less, right? Second, there was a problem. This generation was that much dynamic in nature, right? Without battery storage, it was not possible to make them dispatchable. Right? Dispatchable means I want to send this much power. I have a commitment as a power generation company with some client, and this much power is required. And if I am totally dependent upon these renewable sources, then there may be situation that I may not have that much generation. Right? So these battery energy storages, they make this dynamic generation or non-constant generation dispatchable. Clear? So this is the term you shall remember. What is the usefulness of battery? Battery makes the renewable energy generation dispatchable. Clear? Number 3. Now, the time when I am saying you that we are in the era when we are using this renewable energy generation, so what we are doing? We are trying to be generation following load situation today. In the morning, there is a forecast of the climatic condition, there is a forecast of the solar power generation, there is a forecast of other type of non-conventional generation. Clear? Non-conventional means renewable. Is it or not? Right? And there are problems, several research is going on the load forecast also. If today is this much climatic condition, hot, cold, whatever that is, what will be the load requirement tomorrow, right, or day after tomorrow? Clear? There are considerations for holidays also, there are considerations for working days also, there are considerations of some match or festivals also, there are consideration of during this day time, there are considerations of some popular TV shows also, right? They have to consider all these things. This 8 to 9 is the most prominent TV serial time, right? So these may increase the load. Clear? Because right now the balance of the generation and consumption is all this difference is going to decide the price of the electricity. Are you aware or not? I think Dr. Prashant has taken this consideration, right? So this difference in generation and consumption, that shall not be much more, right? Because this difference, either generation is more, in that case you are not going to get the price of the unused electricity, right? If the generation is less and consumption is more, then the utility companies may be liable to paying some penalty for that. Clear? So this characteristic is going to be very critical for these scenarios, right? Because this all cost which the company is going to bear, that is going to be passed on the customer. So if the company will book loss, so they will not be in the business after some time, or if they are not caring of this loss, it means the customers are going to bear this price. Agreed or not? So that is the reason this particular domain of electricity is under research. Clear? So you as an electrical engineer who are planning to do some research in future or planning to do some project for your BTech or MTech courses, you may take this dimension, right? This is a very interesting dimension where mathematics and your favorite AI and ML techniques, they are also have applications there. You can be a part of that thing. So this is just a motivation how to attract you towards the power system engineering. Means problems are here also where you can apply this AI and ML. Clear? Chaliye. So IBRs are basically solar PV, wind turbines especially type 3 and type 4. What is the difference? I will cover in the next slide. Then comes BESS, that is battery energy storage systems, right? They are battery or some energy storage system in general also. Clear? And then fuel cells, then electric vehicles also. Because what is electric vehicle? Electric vehicle basically is battery on wheels. Agreed? Means if you want to use it as a load, it is grid to vehicle. If you want to use it as source, it is vehicle to grid and it can participate in this complete ecosystem of the electricity. Agreed or not? So key characteristics are, with this non-synchronous power sources is, they provide no natural inertia but can support grid services. What are the new grid services? Earlier the grid service was only to provide electricity, right? No other function this grid system was doing, and it was there only that they have to provide this electricity at with some specifications that this much voltage band is there, etc., etc. And most important thing, they used to take care of the power factor shall not go low, right? And it was never beneficial for the consumer to take care of this power factor, and that's why this responsibility was only with the utility, that they used to maintain this power factor, right? And earlier these utility companies or generate the substations, they used to have this capacitor, right, installed at their substations, right? Can you tell me why this is beneficial for the supply company to maintain good power factor? Do you have answer? Have you studied the course on power system? Have you studied? It's a very simple answer. No sir, it's a very simple answer. Okay. In which course you are? Oh dear. Which college? Okay. Have you covered this first year course? Have you studied that Excel and XC calculations? Have you done those things? Have you done this power diagram, power triangle, active power, reactive power, and okay, you just draw that in your copy. Can you draw it? This is a triangle having one angle of 90 degrees. Just draw it. एक सब लोग ड्रॉ करें प्लीज. Draw a right angle triangle and put PQS, right? P is the active power, Q is the reactive power, and S is the apparent power. Yes, you know it. Just draw it there. Have you drawn it? Okay. Just put a relationship between them, among them, all three. Okay. Right. So we all know that the quantity which is generated, this is what among these three? In S, P and Q, what is the generation? S or P or Q? What is generated? P and Q. किसी के दबाव में जवाब तो नहीं बदल रहे हो? ठीक है. Let me tell you one more question. One more question is, have you gone through the ratings of generator, alternator, or that turbine which you are just telling? Rating of transformer, KVA, MVA, right? Rating of generator, kilowatt, megawatt. Right? So you are making generation in terms of S. Yes or no? Right? Do you agree with me or not? दबाव में मत बोलना, क्योंकि मुझे पढ़ा हुआ पुराना काफी टाइम है. मैं तुम्हें हो सके तुम्हें जल्दी पढ़ा होगा. हाँ या ना? एस में होता है या पी में होता है कि क्यू में होता है? इट इज नॉट इन क्यू इन एनी केस, राइट? So you may have a confusion between P and S. Agreed or not? Okay. Just try to find out the this specification of a alternator. Please try to find out. Open your mobile. Right? Just try to find out the rating of a generator. काउंट करेंगे ना. This is hands on, no? हैं? पक्का? KVA or kilowatt? Includes the maximum output. Okay. But kilowatt is always dependent upon cos phi. Agreed or not?
These are there, synchronous generator and synchronous motor.
When we will talk about generation, we will talk about only SG, synchronous generator, that mode. Right? Okay. Next block is transformer. Transformer is also in MVA, KVA or VA. Agreed or not? Okay. So just now come back to the triangle, power triangle. Okay. So this power triangle says that at this particular moment there is one P, Q and S. Right? We will make S constant. Clear? Now do this. No constant. Okay. Make this P constant, because P is the consumption which is happening at that substation. Agreed? And for that P, which is in kW, kilowatt, right? You are getting the price of electricity kWh per unit, rupees per unit. Agreed? So this P is fixed. Yes or no? Okay. Now what do? You just make it as P Q1 S1. Mark it in that triangle. In that triangle, P constant, P Q1 S1. Right? Now, consider Q2. Q2 is larger than Q1. Draw or change that triangle only. Or you may draw some new triangle also, but on similar base. Clear? So now Q2 is larger than what? Q1. Okay. Now compare the power factor for both cases. It is poor when Q2 is more. Why this is poor? How can you conclude this? Cos phi. Right? Which angle you are talking about? Power factor. Agreed? Power factor means phi is increasing. So S is also increasing. Yes or no? Means when power factor is bad, you are supplying more S. Agreed or not? Okay. Now you control reactive power. Consider Q3 less than Q1. Make it lesser than Q1. Means you are taking care of reactive power, right? And you are supplying this Q locally at substation through the capacitor bank or some other mode. Clear? आप बताइए, अभी तक करंट पे जा ही नहीं रहे हैं. We are simply talking about theta, P, Q, whatever that is. हाँ.
ABR को आप वेरी ABR
जी. हाँ.
तो कांस्टेंट है हमारा, इसका मतलब हम आई नहीं कर रहे हैं, और ये हमारा KBR वेरी.
सर अभी हम केवल वी आर टॉकिंग अबाउट Q. right? There is Q. Then we are, if we go in detail, so there will be two different components. One will be IR, one will be IC, right? IC or IL, whatever that is, depending upon the nature of that, right? So what we usually have a common notation that our loads are inductive in nature, right? So what they are doing, they are IL in nature. Agreed, right? And just to cancel the amount of this capacitive current, sorry, this reactive part, we add these capacitors, right? So they oppose and neutralize and try to dominate. Agreed or not? So this part is reduced. Q is reduced, means when you added capacitor, this inductive part of the Q is reduced. Clear? So what is for the same P, now you are having lesser S. Agreed or not? What is the case here? Power factor improved or not? Improved. So for when this is for benefit of whom? This was for the benefit of the supplier, right? Now for the same revenue in terms of kilowatt hour unit cost, right? He had to supply or he has to supply lesser S. Agreed or not? Clear? So that's why this was usually in earlier days, this was done at clear. But nowadays, when the power electronic control devices are there, your LED bulb or this tube light, whatever that is, they are taking care of this power factor at instrument only. Clear? So this is the second aspect. But yes, agreed or not? Any confusion is still there or not? Clear? So this was the reason why we used to add capacitor at the substations. Clear? But these were the questions of the numericals of the past time. I do not know. Have you your ignorance shows that you are not dealing with such questions now. Is it so? Chaliye sir. So we all know that these generators, we will come back to this, they provide no natural inertia but can emulate this inertia through control techniques or some software, right? So when we are saying that we are adding this control techniques or we are trying to adding some software application over here, so I will again go back to that 3D that was not completed. Those 3Ds are decarbonization, decentralization and digitalization, right? Or earlier I used the sequence. Decentralization means generation at the load point. So when you are doing generation at load point, it means the requirement of the distribution system is reduced, right? So again, the problem of distribution losses is gone, right? And that's why there is a new terminology called distributed generation or DG, or that is also called DER, distributed energy resources. Clear? Now, there is again one more question. If when I am saying DER and I am saying IBR, right? And I am saying that both of them, they are being used for or they are serving the purpose of decentralization. Agreed or not? Then why I am taking these two names? What is the difference between DER and IBR? Can anyone tell? DER is distributed energy resources or DG, right? Second is IBR, inverter based resources, means power electronics is there, right? And again I am using the term renewable energy resources, right? So all these means question is, these are three terms, not different terms. Are they same or they are different? Tell me. Same? Different. What is the difference? PV
Like,
is an IPR. PV is an IBR. What is no type? Nothing like type. They do not require. So they are synchronous generation they are using. Hydro is using synchronous generation. They are using alternators. They are not. The water is not falling on a inverter or this converter or some solar plate. Water is falling on a turbine. Turbine is rotating. This rotating turbine is having some mechanical power output, and this is connected to alternator. That is a synchronous generator. Clear? So that will not come into this category, in this category. That is synchronous generation. Not agree. Agreed or not? Then what is the confusion? Your expression says that you are not convinced. How can you say that? This is renewable energy, right? That's why I am repeating the terms again and again. This is this, this is this, this is this. What is the difference in all these three terms? Right? Now there is a term DER, distributed energy resources, or distributed generation. Clear? Microgrid definition says distributed generation. Microgrids are comprised of distributed energy resources or distributed generation. Right? That doesn't limit it to renewable energy resources. If you go for the definition of microgrid, the standard definition, IEEE definition or US government definition, they are the initial definition of earlier days, or SIGRE definition. Right? So these are the few things where microgrid is defined. Clear? But that uses distributed generation, not renewable energy resources. So let me make it clear to you. When we are saying distributed generation, the distributed generation may contain that solar panel also, that wind turbine also, that battery BESS also, right? That diesel engine also, right? And some turbines are also used, right? Small turbines. Not fuel cell is also there, right? So this is a mix of renewable and non-renewable, right? So if you will read further, you will find that you can say that this renewable energy resources or renewable energy resources is a subset of DG or DER. Agreed or not? So this is the difference. So try to find out the definition of microgrid. There are three definitions of microgrid, standard definitions. Try to find them. Definition of microgrid. क्या हुआ? कॉपी में लिखो ना, सर्च मत करो अभी, बाद में लिखना. Definitions of microgrid, right? And if you will take interest in that definition, you will, if you want to go deeper in that, you will find that this definition of microgrid, which has been released officially, right, and which is followed by the word that qualifies the Edison's first experiment of Pearl Street, right? The Edison, when 1882 or something like that, he did that commercial setup, very first commercial setup, when he commercially made available the electricity on that Pearl Street, right? It was some 11 miles long street. On that, he using the diesel generators, he generated the electricity and provided on that street. Clear? And if you go by that definition of microgrid, that definition has certain points in that, of that geographical boundaries. They talk about resources, limited resources. They talk about they can be used in a grid connected mode, or what is second? Islanded mode, right? In both modes they can operate, right? So if you qualify those conditions on that experiment, that is established, that experiment was a microgrid thing. Clear? There are n numbers of papers available on IEEE Explore where you will, there is a column called history, right? You read that. Very small pages sometimes, but very informative. They will take you back to the history of the electricity, how it was started. Clear? And earlier generation was DC only. Then how and why we shifted to AC, that is also recorded there. And in what conditions or in what situations we are again coming back to DC. Presently what we are talking about, mostly our loads are DC, right? But as the supply available is AC, we are again converting it into DC for our uses, right? So here all these IBRs and other converters, inverters, they have a role. Clear? So that is a different story. Okay. देर तो नहीं हो रही है अभी हमको, have time ना, ठीक है सर. So these inverter based resources, they have key characteristics. They provide no natural inertia that can emulate grid services. Grid services can be taken as inertia, voltage frequency regulation, black start and islanding capabilities, right? Note down these services and try to know about them. What are these services, right? What is black start? What is islanding? You must be aware with this because you are hearing about this since last few days. Okay. Second, they replicate these functions through control, different control methods. They may be loop control or something like that, right? Synthetic inertia or voltage regulation they can provide, and that's why they are important. They have importance in this new type of new system of electricity generation. Then comes rapid control response. Using these control techniques, they are capable of providing the solutions of the problems, right, in milliseconds, right? That is their response time. And these are fully programmable operations. At what level they have fixed some certain this control techniques are involved, right? And frequency, voltage, power factor, they all are controlled in millisecond response time. Then they have this fault limiting capability in them. So they have this, whenever there will be fault, either way they will be isolated or that will be repaired automatically. And these IBRs have two different types. One is grid following, that is GFL, and second is grid forming, that is GFM. We will use these terms GFL and GFM in our further discussion. Now, as I told you, we have a second slide which having this differentiation in wind turbine type 3 and 4. So this is the difference. Type 3 is DFIG, that is, we have read about that. That is doubly fed induction generator. बेटा ये स्लाइड्स की फोटो खींचने में तुम डाइवर्ट हो रहे हो इस समय, ठीक है? दिस ऑल इज अवेलेबल एज a YouTube lecture that is going to be a permanent record, right? And second thing, always prefer to note it down in your notebook. Whatever you note there, you at least that is going once through your hand, right? Or through this ecosystem of brain, hand, equilibrium. Clear? So again, when you will have this notebook, at least you will study about that, or you can ask to me again. So this type 3 is DFIG, doubly fed induction generator, and type 4 is full converter wind turbine. Clear? This is the difference between this type 3 and type 4. Type 3 was having certain limitations, and that is the reason type 4 wind turbines are mandatory in certain power systems in specific countries. Agreed? So what is the difference? First feature is generator grid connection, right? Only 30% power is processed through rotor via converter, or stator directly to grid that handles 70% power. And this 30% is only managed or controlled or adds flexibility in the wind power generation, right? Whereas in case of type 4, the generator is fully decoupled and all power is processed through this converter. So it is fully controllable. Clear? Second point the same, that is the speed control. And in that case, when the control is applicable on the rotor part, in first case, so only limited range variable speed is available because you have a control on the almost 25 to 30% of power. Clear? But in case of second, you have a full range control. Next point, bit interaction is, so this type 3 is having GFL, type 4 is having GFM. Control over active and reactive power, again partial is there, so this is indirect control. Direct control is only on 30% generation, remaining is indirect. Direct and full control on the complete thing. Fault right through capability, okay, note it down. What is the term? What is the meaning of term? Fault right through capability, FRT capability, right? So please try to identify these terms in between. What is the meaning, right? Otherwise, I am telling a story about Ram, Shyam, X, Y, Z. You must be known with the characters, right? So these are the participants of this story. So what is FRT? Please be aware about this, right? If not, we will discuss again. So this capability is limited in case of DFIG or type 3. Type 4, this is strong capacity is there. GFM or black start capability, this is not supported. That is fully supported, means type 4 can or may supply electricity to a dead grid, right? That is the condition which we call black start. Clear? So black start is that. Typical use is type 3 is older wind farms and cost driven projects because type 4 has a higher cost, right? So low capacity or low capability, low ratings still they are available in DFIG. Where the commercial ratings are available with full control thing, they are this type 4 and mostly offshore winds which are not easy to access every time for control or for maintenance, etc. There only these type 4 wind turbines are preferred. So why we are having this much discussion about the IBR, right? Earlier there were confusions ki no, this thing is not going to happen. Whenever we have something new in our system, first we have a doubt on that. Is it going to happen or not? Right? Very long back, in 87, when I was taking my admission in BTech, at that time we are that doubtful because computer science is going to be a successful branch or not. Most of us didn't prefer that, right? But I am a graduate of 91. Before 2000, every person who did BTech computer science, they were doing very good. They were comparatively much better, you can say, or economically, not in other ways, right? And when this 2000 year come, that was a problem like Y2K. Are you aware with that problem? Have you heard of that? Of course, basically, most of you are born after 2000, I think. Most of you, right? So there was a problem that was called problem Y2K. Means earlier it was 98, 97, 99, and how the computers will behave when this 2000 and that series will open, right? So that was the problem Y2K. Clear? So similarly, what is the demand today? After 87 to today is 25, almost 27, 40 years, right? And after some time, every boy wants to go for the computer science only, right? That is also not a good trend. I support that. It is not a good trend. It is a very dangerous trend. Anyhow, I am thankful that you are studying electricity because this power is very much important for the of this for running the show in the society, in the city, in this globe, right? So that is very important thing. So in the same way, there were hue and cry about how it is possible that all the grid is going to have zero inertia. Means no generation through coal, no generation through synchronous generators or synchronous machines, including hydropower. Clear? But these are the few examples where this Hawaii, USA, they have this 100% IBR generation they had with for some time, for short durations, they have maintained that using this battery energy storage, advanced inverter control functions and careful dispatch planning. Means you have to make the electricity dispatchable, right? As I told you earlier, so all this energy systems control, whatever that is, that was properly managed. Hawaii targets, Hawaii means Hawaii Island, they target 100% renewable energy by 2040 with real world IBR trials underway. Second, India is also having their own targets, right? And we are having a target of achieving this net zero by 2070. Are you aware with this or not? India is also having its own targets for generation of solar power and wind power by year 2030, right? And in end of every month, Ministry of Power, they release a data on their website how we are achieving our targets, right? And at the end of every month, they show it, yes, we are ahead of our targets, right? So it is very much possible if whatever we are targeting for 2030 or 2070, we are going to achieve them quite earlier. Clear? Second option example is Ireland. They are operating with more than 75% generation of IBR, right? Means renewable energy based generation is there, which is using these power electronics in this processing of electricity. Number 3, most of the countries, especially in Denmark, they are having this wind power generation capacity, not generating, right? They have this wind power generation capacity of 120% of the maximum demand of their country, right? If they have a requirement of 100 megawatt, they are generating 120. And that's the reason most of the countries in Europe which are near this seaside and they are having this good wind profiles, they are generating a very large amount of electricity, and the whole Europe, they are interconnected. And that is the reason sometimes they are enjoying very low prices of electricity also, right? Germany, they are dependent on solar power, right? And let me tell you a story. In Germany, some 2-3 years back, I do not remember the year right now, or maybe 4-5 years, right? At the end of the year, in the month of December, right? December was the month when the Christmas is there. Agreed? Christmas is a festival which they enjoy a lot. And most of them are traveling. No office, no business, right? And once they are traveling, so this residential load is also down. Clear? And here comes I will cover this topic grid codes also. And here comes the role of grid codes. So you must be aware with the term grid codes also. What are the grid codes and how much important role they have in the operation of grids, right? and especially in those grids which are IBR rich. Clear? Again, IBR rich means this volatility of generation is going to be different. So what happened? Through this prediction, they found that the solar generation is going to be very high in some particular days after 25th. That was probably 26th or 27 or something like that. Right? So, when the generation is going to be very high, consumption is going to be low than average. It means there is going to be some unstable things in the grid. So, just to avoid the damage, either you have to disconnect the things, and once they are disconnected, again the problem of synchronization, etc., right? So, what method they adopted, that is also a legal method nowadays. They published that for this particular duration, we are going to offer, or they published means they communicated this to the customers, right? For this much duration or for this much on these dates during these hours, right? We are going to have this negative electricity prices. Means if you are going to consume the electricity, you are going to earn some revenue, right? Dr. Prashant will tell you much better regarding this because he is a man of electricity market. But this is the story which I have read, and that was a very new thing for me at that time, right? So that's why I want to share. I hope you also have listening it first time. This is the terminology also available in the electricity market. Clear or not? How many of you are aware with this term, negative pricing, except Professor Tiwari and Mahima? You also know. Good. So ठीक है भाई, इन तीन आदमी के अलावा बाकी लोग नहीं जानते थे ना, सुना कि नहीं सुना ये बात? दिस ऑल्सो हैपेंस, तुम भी जानते थे, ये सब जानते थे यार। ये तो भाई देखो बारी बारी तैयार होते जा रहे हैं यार। चलो कोई बात नहीं, जो नहीं जानते थे उनके लिए जानकारी है, जो जानते थे वो और जाने इस बारे में कि what parameters are there, such parameters are there. Then this is this is also a part of European grid, Irish grid. This has hit instantaneous IBR shares up to more than 25% and aim to 95% plus by 2030. Implements SNSP limits. SNSP is system non-synchronous penetration threshold. At this stage, we are not going in detail of this term. This is just for your knowledge, right? So, and as the total generation is non-synchronous, so they are having this synthetic inertia via wind and battery energy storage, special operation controls for frequency and voltage. So, why we are discussing at this point here? The purpose is to just to tell you that high IBR operation is no longer theoretical. This is taking place in practical, right? So, high HBR grids are already being operated reliably. When the right mix of control strategies, storage required for dispatchability, right, and grid codes, even 100% integration of IBRs in the grids can or do work reliably. Clear? So, next term is grid codes. Why the grid codes are evolving? I told you grid codes, right? And in Europe, most of the countries, they are having their own grid codes, right? Because same thing is not going to applicable. One, what is that saying? Ki one doesn't fits all, right? One solution doesn't fit all. Clear? So, there are some standard of global or international level, and each and every country, they have modified it as per their requirement. And that's why this is the reason every country is having their own grid code. German code and other European countries code, they are very popular. So, what are grid codes? Grid codes are basically checklist. जब आप when you leave the room or your home or your room for the examination, you have a checklist. I card, yes. Pen, yes. Similarly, grid code is also says voltage in this range, fault no, current this much, power factor this much, and they are more important in case of faults. Means something unavoidable and unwanted is happening in the grid, right? In that case, you can monitor, yes, up to this point of operation, we will have to wait. We can operate, right? And once this particular line is going to be crossed, then we will disconnect this particular portion to save the remaining portion of the grid, right? This is the, or in what conditions something disconnected earlier or some new generator that can be added so that the balance of this running system is not going to destroy. Okay? Whenever there is a new load, big size of generation or big size of consumption, they are added in the grid. They have to pass through these grid code requirements. Agreed? So the purpose is define the technical and operational requirements for all grid connected generators. Grid codes are issued by grid operators or national or international regulatory authorities. Focus area is normal as well as abnormal operation, both, right? Abnormal system conditions, and they measure fault response, voltage and frequency behavior, right? We will take a consideration of term rate of change of frequency in our later discussion. So his response of frequency behavior, how this frequency is changing, that is also considered here. The key function is ensure that it remains safe, stable and reliable. Stability is very important. Either it is a synchronous grid or non-synchronous grid. You are aware with the course. Stability, I hope you all are aware. Most of you are aware. Agreed? Then, especially during disturbances or contingencies. Why grid codes are changing? Grid codes are continuously changing. They are evolving continuously with the new scenarios upcoming in the grid, because new type of loads, new types of generations, new types of storages, they are connecting in the grid every day. So the power grid is shifting toward IBR based generation. Traditional codes were built around synchronous generator or synchronous machine operation with natural inertia of that machine and the grid support. Clear? Modern power electronic based inverters need explicit instructions to behave like supportive elements, and those instructions, they come from the grid codes. Clear? So, what are the new expectations from the grid codes? What they shall, भाई आप एक रेफरेंस किताब खोले, भाई ये देखना है, इसमें हमने आपसे कहा FRT देख लीजिए, तो सब FRT तो है, लेकिन इसके क्या रिक्वायरमेंट्स होने चाहिए, क्या कितना क्या वैल्यूज होने चाहिए, that is not mentioned, right? So that is the expectation from the grid codes, which are new in nature. What is the fault right through capability? Reactive power support during faults means abnormal operations, situations, inertial response capability, and voltage source behavior or grid forming ability. So these are the new expectations. The global challenge is several grid codes, they lack detailed definitions for IBR behavior, because nature of IBR is changing every day. Clear? Controls are changing every day. No uniform requirements for GFM control. Inertia emulation means copying or developing inertia, or harmonic absorption. Harmonics is also a problem. When you are going to introduce power electronics in the grid, right? Definitely this is going to have some power quality issues with it, right? You have to take care of those aspects also. Then enforcement often falls to individual TSOs. TSOs are transmission system operator. This concept is present in India also, and very soon we are going to have these DSOs also in the system, that is distribution system operators, right? So who are new to this term, they must know this, what is TSO and what is DSO, what is their role, right? And how this, why this DSO is going to be or they are going to appear in our Indian power system. Now what is the need here, and then you understand what is actually happening in the power system nowadays. So IBRs can behave differently, and in different countries, different scenarios, different types of IBRs, right? And grid codes are evolving to push them toward grid forming behavior, not GFM. So this is the comparison of this grid following or grid forming IBRs. Frequency reference, this has been compared on the aspect of frequency reference, voltage source capability, synchronization, inertia emulation, fault ride through or FRT, black start capability, control architecture, role in weak grids, real world adoption, and suitability for 100% IBR grids. Most of these points we have already discussed in our discussion, right? You can just go through this table, right, and try to conclude कि whatever we have done is summarized here or not. If any new point is there, you can ask. ये वाला था. Thank you, bye. Thank you. Any question? Can we move? Weak means what? Inertia. और क्या हो सकता है? Electricity cannot be weak. Either 10 volt or 20 volt, 100 volt, whatever that is. Yes or no? What is more dangerous, like voltage or current? Sure. They are equally important at point of consumption. I am talking about danger, electrical safety. Which is more dangerous for the human being? Electrical, higher current or higher voltage? Why? Read about it. Okay? You just Google electrical safety, right? And always trust on the reliable resources, right? So I always suggest for the IEEE Explorer. You will immediately find which is more dangerous, but trust on that official document which is available on the IEEE Explorer. Here, then have some questions. We will discuss it tomorrow. I am open. Here. So this particular table concludes that grid forming IBRs are essential to grid as per the new requirements, right? Because of these advantages which are being listed here in this table. Clear? And they are essential to grids with very high or full IBR penetration, as we are targeting towards that 100% penetration. They replace the core functions of synchronous machines in software, making them the foundation of tomorrow's stable and fully IBR based grid. Challenges in high IBR bits. What are the challenges? In terms of stability, protection and control. Because these are the three aspects with which we have to handle to make the grid stable, safe and reliable. Clear? So, challenges are no inertia, how to handle it, no rotating mass, and when rotating mass is not there, so this rate of change of frequency is going to be very high. Yes or no? So, that is unstable frequency. That problem may cause due to lack of inertia. Second is weak frequency response, means GFL, means grid following IBRs, mid column, they do not inherently regulate frequency, right? GFMs do. Loss of natural damping. Traditional synchronous generators, they provide passive damping. IBRs don't, and they require active damping through control algorithms. Clear? It is possible to have, but for that we have to employ control techniques or active damping methods. Voltage instability means weak grid, that goes to poor voltage support from IBRs. Dynamic weakness, that is fast but fragile behavior, and problem is it is difficult to model. When modeling is difficult, then definitely the finding solutions are also being difficult. Clear? Then protection and control challenges, low fault current. IBRs can not supply high fault current due to limitation of the current capability of the components. Clear? Then comes relay misoperation, means legacy protection techniques which are mostly for the AC grids, they may fail to detect IBR faults. Coordination complexity, IBRs are dispersed, means distributed generation. Clear? So varied controls, latency, bandwidth requirement for control, because it is very difficult to have a centralized control for them, right? So you have to put this control at local levels. Small signal oscillations, the control interaction is in the band of 1 to 15 Hertz. No unified load sharing, means no frequency based governors like coordination. So this is a challenge to handle. In high IBR grids, system security depends not on inertia because it is not present or any hardware, but it depends on algorithms, faster control and coordinated standards. They control and they try to maintain our grid reliably for the reliable operation. So why the GFM is the way forward? Traditional IBRs assume a strong grid for synchronization and fault support. In high IBR or weak grid system, definition is here. Clear? GFL modes fail to maintain stability, leading to protection issues, voltage collapse or poor frequency regulation. In GFM IBRs can directly address lack of inertia by emulating inertial response through control. Grid voltage collapse, they can be controlled to act as a voltage source right through capabilities. So through control they can remain stable throughout the fault and normal conditions, and they can provide this they have a capacity of providing this black start flexibility, means they can energize dead grids independently. Clear? Write down a term. What are the ancillary services? there is a term ancillary services. Read about it. What is it? Okay, what is it a single ancillary service means single service, or it is a set of services means multi services are coming under this umbrella term? Clear? So please read about it. Core capabilities of grid forming IBRs, GMF, this grid forming IBRs, they have a feature of voltage source behavior. They provide controlled magnitude and phase, and that enables grid forming. Virtual inertia they can provide to stabilize frequency and lower down the rate of change of frequency. Means once you are adding the inertia synthetically, the rate of change of frequency is going to come down. Black start capability, reactive support during faults. So this reactive support that is going to support the voltage or voltage drop, it can be taken care, right, and contribute to system strength. Harmonic and unbalanced mitigation they can do, right. So they can provide this waveform stabilization, or this waveform can be maintained, or quality issues can be removed. Then comes first swing or emergency damping, means they contribute to transient grid survival after major disturbances. Means damping they can also provide. Means whatever were the problems with the removal of inertia from the power system generation, that can be taken care very efficiently with these GFM based IBRs, right. So they are nowadays can be treated as a complete solution of this problem, right. The only way is how to provide or manage a better control of them, right. So next solution, next research is on how to develop the better control techniques for using these GFM based IBRs. Clear? So practical challenges in implementing GFM is current limiting constraints are there, because these polyphonic controls, they can have some current limitations with them. So they can typically only operate up to the 110% of the rated currents of the system, and sometimes fault currents are much more than this 110%, right. So that is the issue. Limits fault support and inertia injection during events. Simplified control models. GFM dynamics are based on mostly first and second order systems, right, but practically they are not, right. These control systems or their control models, they are typically having much more higher order, and using this what this they use, Deepak and team, model order reduction, right. They bring it to first and second order. Unlike system generators having richer dynamics affecting small signal and transient stability, जो कि SG ना होने की वजह से नहीं है, that is provided, that is a challenge for them to provide. No global GFM definition exists right now. There is a standard I will talk about that has been introduced in 2022, but still TSOs means transmission system operators, who are the responsible persons for operating these grids, right, means major portions of the grid at the country level, right, they face this problem sometimes, right, and mostly these problems are more dominant at the points of interconnection when the electricity is going from this country to that country, right. So those point of interconnections, if the countries are having the different grid codes, then this is definitely an issue, right. Suppose you are going to solve that problem temporarily at the point of interconnection, but if the operational requirements are different, so you cannot be very sure the problems are not going to appear in future at some different point of time with some different set of operation constraints. Clear? So that is the issue. So that is written as inconsistent grid behavior. The control complexity, again, when you are going to add damping, active damping or something else, right? All the behavior you are going to emulate or imitate there using through control techniques or software. So definitely that is always a control complexity. We will explain it further in the next slide. The GFM closes the functional gap. However, we can say that GFM is a possible solution which can be explored further to bridge the gap between this inertia and non-inertia based power system. The design level control complexities in grid forming IBRs are GFM behavior, the same points, just some you will find some one or two new points in that. It is GFM behavior is controlled or software defined. Parameters like inertia and damping are not physical but must be designed and tuned, means emulate. No use of PLL means phase lock loop is not there in GFM, it was in GFM. GFM must self synchronize as a voltage source. So that is also a challenge with GFM. Requires careful tuning of virtual inertia constant because it is going to affect rate of change of frequency. Yes or no? It is going to affect frequency. Damping factor, you have to tune that. Angle synchronization, you have to tune that because these all are required for the stability of the power system. So why it is challenging? Dynamic behavior varies with the system strength and topology. Why I am saying this? Because when we are saying that IBR based system means now there is no requirement of adding some 500 megawatt system in the generating station in the system. I will have 1 kilowatt. I am getting subsidy for this 2 kilowatt, 3 kilowatt and 4 kilowatt for this rooftop solar from the government at different rates. So as per my capacity, I will add either 2 kilowatt or 3 kilowatt or 4 kilowatt, right? So I can connect it to the grid. The local substation is also going to connect my system of rooftop with that. Yes or no? So definitely not today, but after some time, when this sigma is going to high, they are going to bring some difference. Otherwise, how much power a TV consumes? Television? How much power? 100 watts. 100 watt was a time when that was CVT. That was older time when there was a picture tube this size, right? अभी तो टीवी इतना पतला सा है, हाँ? चलिए पता करिएगा, मुझे आप सवाल सही है उसने भी जो किया, मैं छोटे और बड़े में कितना कंजम्पशन है डिपेंड्स. नहीं, साइज ऑफ पैनल से बहुत फर्क नहीं होगा. चलिए ठीक है, देखिएगा, ये भी एक क्वेश्चन है. ठीक है, एज इलेक्ट्रिकल इंजीनियर आपको यू मस्ट बी अवेयर विद दिस कि हाउ दिस व्हाट इज द कंजम्पशन ऑफ दिस ओल्ड फैन एंड द न्यू फैन. न्यू फैन मीन्स व्हेन आई एम टॉकिंग अबाउट BLDC फैन, right? How much consumption they are doing? Most of the time, if I ask how does a meter work, meter means electricity meter, you will say yes, I know. But the meter which you know is nowhere installed right now. How many of you are aware with the smart meter functioning? Are you aware with it? You must, because you already done a course in the measurement, right? So you cannot say, no, I have read this old Sahani book and that's why I am aware with that. Net meter is there, yes. When I am talking about this thing, na, connection at the rooftop with using government subsidy. So there is net meter also connected in the power system. Here, you must be aware with these things. If you are having a meter, I think most of us have a meter in our home. Yes or no? Is there anybody who is not having a meter in his home? Right? So, you must know about the electricity meter, what it is doing. Right? When you have this, as I told you in the earlier days, this capacitor connection was the responsibility of this substation only. But right now, you will see that electricity meter is this long. Yes or no? A paper slip of some 2-inch width, but long maybe 12 inches or 15 inches like that, right? And you just try to read the entries in that. Have you ever worried about that? What are the entries in that? So now you are not paying only for the kWh, you are paying for n number of things, right? And that those things can be avoided, those payments can be avoided if you just see for which item I am paying, right? Maximum demand. Are you aware with that? Every consumer is paying nowadays. There is a power factory entry is also there. I am not sure ki are they charging for that or not, right? So just try to read your electricity bill. That is a very important thing, right? So please, if you are not having a bill, if you are having a meter but not having your access to your bill, please try to take it from your friend or your neighbor, right? And just try to understand it. What this electricity meter or this report bill, right? Which items it is having. Clear? Definitely it will add something new in your knowledge. Clear? So next comes the system operators, because they are the real persons who are responsible for the successful operation. And by this new additions of IBRs at different levels, right? Earlier these TSOs were responsible because these are new resources of generation, they were added at the transmission level only. But right now, when you are having this connection to the local level and distribution system also, so definitely the DSO has also become important. They have also become important, right? And very soon this Indian system is also, they are having TSO right now, but DSO is going to be added very soon. It was decided in 22-23 like that. There was a report of Ministry of Power. This IIT Kanpur and REC Jaipur, they were NIT Jaipur, they were the part of it, right? So this Terry was also a part of that. So they have submitted their recommendation that DSO role, what is the role of DSO and why they are important in this new power system. So government has accepted that report. Let's see when it is going to be added in the Indian power system. So this TSO expectation is right through faults with voltage support, act as harmonic or unbalancing, support LFDD schemes, LFDD I have explained below, then eliminate PLL dependence, right? So first is right through fault with voltage support, that maintains stability, that is N-1 or N-2 reliability. Are you aware with this term? Are you aware with this reliability? A system is having n number of components. What is going to be, how this is going to affect the operation of the system? If system is going to be operated with N-1 component, means some one is not working, or N-2, two are not working. Clear? So try to get information about that also. What is N-1 and N-2 events? Then act as a harmonic or unbalancing. We all know that power electronics is going to add something new. They are going to deform the wave shape, right? And this wave shape deformation is a power quality event. Any type of deformation in the wave shape is a power quality event. Then support LFDD schemes, means frequency remains recoverable in case of load shedding. Eliminate PLL dependence, phase lock loop, that is PLL struggles in weak grids. GFM, they are capable of self synchronization. So what is LFDD? LFDD is a protection scheme, basically that automatically shuts down when system frequency drops dangerously low, means ROCOF is high, clear, caused by generation load imbalance. Why it matters in high IBR grids? Because high IBR systems lack HY inertia, frequency drops faster. LFDD must operate quicker and more precisely, that is load frequency demand disconnection. Grid forming IBRs can help delay or reduce the need for LFDD by injecting virtual inertia in the system. Virtual inertia is going to change the control the rate of change of frequency, right, and providing fast frequency support. Benefits of GFM in this LFDD, that it slows down the frequency delay by adding possibility of inertia, possibility of adding inertia. It reduces blackout risk, means system is going to be disconnected. Busy time, wise time for load shedding. In this process, during this time, you can decide, operator can decide which load is to be disconnected, which is the faulty part, and it will save the remaining system, right? Supports frequency based disconnection coordination. So in summary, you can say this LFDD is a last resort defense or a safety net when things go wrong. It saves the remaining part of the healthy part of the system, and it allows you to disconnect the faulty part or unstable part. So this GFM IBRs, they help make it smarter and more effective. There are 3 different types of classes for GFM control: class 1, class 2 and class 3. Class 1 is basic voltage source, no inertia or droop response. Class 2 adds droop control and inertia emulation or support, artificial support. And third is full dynamic support with voltage inertia, fault, harmonic and synchronization, self-synchronization, right? So all GFMs are not equal. Class 3 represents the most complete and TSO aligned version of the GFM behavior. Clear? So what this class 3 GFM IBRs can do, as we read in that summary sheet, that it can provide all those functions. Class 1 and class 2, they are not capable of providing all the functions, right? So these all functions, they are being supported, they are listed over here. They are being supported by the class 3 GFM. So where we are heading towards, right? Evolving global standards for IBRs. So why standards are important? We are coming to the last phase of the lecture. What are the standards? I hope few of you must be aware with this. What are the standards? And who are doing research or some advanced stage of the study, they must be aware with the standards also, right? There are standards for power quality. There are standards for the harmonics. There are standards for the several events in the power system, right? And most of the time, these standards, most dominant standards are either from IEEE in American part of the globe or SIGRE in the European part, right? And remaining countries, most of the countries, they participate in the formations of those standards, and then they try to align it with their own country's requirement. Clear? So IBRs are now central to power systems, but software defines their behavior. Software means control, that defines the behavior. Clear? And without standards, response to faults, voltage dips, frequency events can be inconsistent. So they are more like grid codes, you can say, right? The standards are for the grid codes are for the operation of grid, and the standards are for the devices, basically, you can say, right? So these are the grid code, these are the standards for the IBRs. Clear? So with all these capabilities which we have studied in last slide and second last slide, right? But this clearly summarizes that GFM is a new baseline for high IBR systems stability. Do you agree with it or not? Means when type 3 is providing you all the features, so that is capable of making the system, power system, equivalent to inertia based systems. Clear? And even inertia based systems were requiring some specific type of control for maintaining the stability or maintaining the frequency response, voltage regulation, etc., etc. And all those things are being covered by these GFMs. Sorry. Yes, GFMs. Clear? So the key standards and global initiatives are, in USA there are different bodies, FERC, NERC, they are there. And this IEEE 2800 standard is also there, which was released in 2022, right? So this IEEE 2800, that contributes performance based IPR specifications, voltage, frequency, FRT and harmonics, right? And these NIRC guidelines, they are operational guidance for IBR fault and voltage events only, right? So they are not the complete one. Europe is ENTSOE, that is network code revision, that is underway, it is going on. Drafting pan-European GFM specifications for IBRs. Then comes the Australia, the grid forming requirements. Australian system is having mostly they are dominant with the solar power systems, right? Because they are having the solar requirement, the solar setup is more, and it is their problem also. Sometimes their more research is focused on these things. Means solar related problems. Clear? Then comes the Ireland, that is the grid, SNSP rules and GFM mandates. I already told you what is SNSP, that is system non-synchronous penetration threshold. They are tying IBR percentage targets to GFM upgrade reliability, how much percentage of IBR can be increased. Why not to, or how can we make it to 100%? Then I told you example of this Irish grid also. They are trying for 100% by 2035. Then comes the UK, United Kingdom or Britain. Contracts for GFM services are there. They are under process and they are procuring GFM for battery energy storage systems to stabilize grid after the retirement of coal. Means most of the coal-based plants, they are very old, right? And now they are not going for reinvestment in the coal and they are trying to retire them one by one, right? And if you go in detail of that also, what they are doing with the remaining space of that thermal power plants, retiring the coal means you are not going to make some tourist spot there, right? They are trying to convert it into a space for battery energy storage, right? Just look at it. If they just try to locate how many old thermal power plants, coal-based power plants, they are being converted for the battery storage, right? So this is also an interesting thing, how they are converting those thermal power plants into battery storage locations. So this IEEE 2800 and why it matters, this defines maximum performance and interconnection capabilities for IBRs in bulk power system. They are applied to all IBR technologies, means all sort, right? And they are going to the limit of HVDC also. Focus areas are voltage and frequency right through, reactive and active power control, dynamic voltage support, fault response, and harmonic management. And they ensure IBRs behave like grid supportive assets, not just energy sources. Means they are emulating the grid similar to the older version of the grid with proper control, reliable operation with maintained stability. What does IEEE 2800 require from IBRs? What information they need and what actions they demand, right? Ability is frequency right through and requirement is stay connected and inject power during deviations. Clear? So grid codes of the European countries, as I was asking, every country is having their different codes, right? So they decide at what point of this code, there is a grid codes plot, at what time of this plot you can enter in the grid or you can leave the grid. This is a mandatory condition for the IBR based generating stations, means these DGs. Clear? And IEEE 2800 is a next stage in that series or in that direction you can say. Voltage support, maintain dynamic, and this inject power during deviations, when to connect, disconnect. That was the reason, that German example I told you, right? They have to give this negative pricing, otherwise they may decide to leave the system also. We will do the synchronization again, but it is not that easy from the regulatory point of view. Voltage support, maintain dynamic voltage, reactive power during faults, fault right through, that is right through low high voltage events, support recovery, inertia emulation, respond to rate of change of frequency using control based virtual inertia, harmonics and negative sequence voltage and current, means unbalanced situation, agreed? So mitigate system distortion, act as a sink to harmonics, active and reactive power control, precise power modulation per operator command. So these are the interconnection process for the IEEE 2800 standard. It gives you how this connection and disconnection of the IBR based system will take place, right? So this we will discuss sometime later in detail. This is the global alignment with the IEEE 2800 principle. USA is IEEE 2800 is active right now since 2022, becoming FERC aligned. NERC supports integration, testing ongoing, means limited only. Europe, ENTSOE drafting GFM specs, they are in alignment. VSM integration is alignment. No pan European Union standard yet. So they are trying to develop it. As I told you, they are in process of development. I told you when we were discussing this pan European standards. UK, ESO contracts GFM by yes with the 2800 like specifications. This UK also has, means we are talking about the alignment, clear? And the operational projects like Harmony and GSRP, they are the projects name through which they are trying to develop themselves. Australia, AEMO mandates GFM for BESS grid support. They are only allowing this type 4 wind turbine in their system, no type 3 or similar to that. This test beds like Honsdale follow 2800 style requirements, clear? So this Australian grid network is very interesting. In European side you can find this German grid code very interesting. They are the toughest code, right? Means sometimes whenever you submit something for research purposes, they give you a comment key, just test it on the German grid code, right? So that for FRT or LVRT, whatever they are, they try to test on that grid code only. That is the final status. Yes, if it is working on this, it will work anywhere. Then comes Ireland. SNSP roadmap requires IBRs with GFM capabilities. Remark is GFM is enabler for more than 95% penetration of these IBR based systems. Challenges, they are modeling burden is very high in case of this RMS, EMT, fault and dynamic test. So all these need to develop models for these studies, that is still either ready to start or they are going to happen but not present yet. No unified global certification process is there. Cost for inverter upgrades, testing labs, tuning, etc. they are very high. User pace to adoption varies, and definitely the risk compliance gaps are also there. So need for TSO coordination on model validation and benchmarking is still a challenge. As I told you, whenever there is an interconnection issue, they may create some problem. So unless until they are not going to an agreement on different codes at certain points, this problem is definitely going to persist. And so current gaps are no harmonized compliance or testing framework for GFM control, lack of common models for small signal and EMT analysis, difference in the FRT threshold for different countries, harmonic handling and inertia specifications between countries, need for convergence on control tuning benchmarks and validation metrics. The standards are no longer optional, they are mandatory. The future of reliable power grids lies in a standard that requires IBRs to behave not like as a component in the system, but as an asset in the system. These are the few references you will find, and definitely if you want to go in detail and want to have some knowledge, I have not went into in detail, much detail of everything. I have attempted to give you only a strong overview of all the aspects, different possible aspects, right? It was more like a buffet system. If whatever area you find interesting, you go deep in that. Clear? So this was all about this. And if you are more interested in those things, you can find out different magazines. Right? This Power and Energy magazine, most of the time you will find that they are the only references I have used. Right? And these are the energy magazines which are giving you the knowledge of the things much in advance. Basically, research publishes after it's happening and reviewing process. So most of the time researches are they are 1 year minimum later than the happening, right? And these magazines, they are giving you updated knowledge, right? So if you are an electrical engineer interested in the domain of power and energy, power electronics, or in general in engineering systems, you can go through these IEEE magazines. Most of the time they are available, freely available on the website, or you can approach your friends who are the members, through them you can get these magazines. And if you are not finding it anywhere, you are finding something interesting, you can come to me, right? But these are the magazines. Try to find out, every quarter they usually publish. Try to focus on any 1 or 2 article of your interest. It is not possible that everything is of your interest. Yes or no? Right? So whatever is you are having interest in that, you mark that, try to explore and deep in that, right? And then definitely when you are going deep in that, you will feel yourself attracted to the connected things. And this is the way by which knowledge grows. Clear? So this is the thing which I want to share with you, right? First thing is, knowledge always comes by the reading. ठीक है? कि YouTube पे देख के कोर्स अगर कवर किया भी है भाई, तो please try to follow one standard book for each and every subject. That is mandatory thing, right? Even if you feel that it is not important, on my advice, have a copy of any standard textbook with you. So whenever you feel कि I shall clarify myself on this point, there shall be someone to support you. And this support, the best support you can get by some good book only. Okay? This is a global problem nowadays. Whenever you are having some PhD interviews or some interviews somewhere else, and it is asked which book of control system you have referred, right? And candidates are not having the answer for that. And if someone tries to play, yes, I have read this book. So never forget that there is an expert on the other side of the table who is dealing with you, right? So sometimes if you are not knowing something, to accept that is a better answer than try to emulate like this GSM, yes, I can do this. That is always a wrong choice, right? So this is an advice for you. If you have any questions, we can discuss. Any questions? Or something like that which you feel that I shall add in this these slides. Sir, everything was covered, but this point was not covered. What do you say about that?
But you have covered all the possible aspects.
Yes, that's what I'm saying. That I have just offered you a buffet, right? I have attempted for that because all this combination was all possible aspects. I tried to collect it. What maybe in which dimension you can go deeper, that you have to select. And if you feel that I can help you in, you select one thing, right? If you feel that I can help you in that deeper journey, I will be there, right? You can write me on this email ID. Acha, email ID is not here. This is Asheesh at MNNIT.ac.in. Asheesh is having double E, MNNIT is having double N. Clear? So please take care of this, otherwise there may be a possibility that mail is not reaching. Right? You can contact me. You can ask questions anytime. At any point of time you feel that this answer I shall give you this answer, I will be there. Clear? I have also please Few total questions I have also developed, Prashant ji. If they want to take benefit of these questions, right? I'm not asking that they shall answer it to me, but definitely if they just go through these questions, they can review whatever they have read, and they can also identify that you are asking it here but not covered in the lecture, right? So this thing you can take care of it, right, sir? Any questions? Any questions? So this was a wonderful audience. I was not thinking that this all will be covered in 45 minutes or 1 hour, where 20 slides were there. But the initial participation they have shown. No issues, no issues. Initially, everything is full with inertia, right? And then after some time you feel, yes, this inertia can be removed, right? And what is the useful part of that? That can be emulated to make a better system, right? And just try to understand this analogy, and this fits on you also, right? I'm not saying that this inertia of not asking the questions shall finish today, but please decide, yes, this shall finish. When this inertia will go, then you will start participation, right? Participation is important. If we are in discussion, so this discussion shall not be one-sided, right? It is not like this that I am having too much knowledge. I am not having any knowledge. I am just disseminating the knowledge collected from somewhere, made these slides and just delivered to you, right? So this is my way. If you are participating with me in the discussion, this may be a better way of learning for me also. There may be certain questions which I may not answer at this instant, right? But definitely if I will have that question, I will bring that answer for you, right? Bilateral, yes. So please ask questions, right? Wherever you are. भाई तुमने 2 घंटे पौने 2 घंटे किसी को सुना है यार, और एक सवाल नहीं आया तुम्हारे मन में, चलो कोई बात नहीं, अपनी कॉपी पे एक एक सवाल लिखो, एक सवाल लिखो जो तुम्हारे मन में इसको पढ़ने के बाद आया हो, कुछ भी लिखो। एक पैसे की काम की चीज नहीं थी सर, आपने जबरदस्ती पढ़ाई हमको, यही लिख दो। हाँ, कंफ्यूजन RER is what? हाँ, IBR. Inertia based resource is inverter based resource is when you are trying to connect it with the grid, right? No. What? You are having a solar torch, you are having a solar calculator.
See, solar and if you want to interact the same with the grid, what we need? Power. Directly you can connect. Yeah, water is there. Otherwise, if something you are connecting from AC to AC or AC to AC, both the cases will need converter or inverter. Alright, or a current resistor involved here. So, any point of time, if you need any power electronic based devices, okay, that will come under that. Right? Yeah. I guess the broader concept in which you can consider the same as umbrella, and with that umbrella you can take it. Right? So we are not talking about the direct connection of renewable energy based system. Inverter, what is there?
अच्छा आप ये बताइए, एक सवाल आपसे पूछता हूँ, पावर साइंस तो सबने पढ़ी होगी ना, हाँ या ना? What is the importance of power electronics? this motor we are using for motion since long, and we were having the very good control techniques for the speed control of motors. Yes or no? Clear? Then what this Powertronics has added in that? Everybody is trying about the power electronic based control. We are having a course also here, control techniques in power electronics. Yes or no? Right? So what wonder these two combination of Powertronics and control makes with the similar machines? Same machine is there. Yes or no? This new generation machines are coming in last 20 years, I think. But earlier to that, when Powertronics was controlling the older machines only. Agreed? So what this power electronics had added? What is its advantage? बोलिए. Low power consumption. Agreed? Why?
Because they operate in a low value of current.
So how this low value of current is? This low value of current is definitely deciding the low power consumption. But main thing is that how this low amount of current is making the things happen in a similar way or a better way. Yes or no? ठीक है. I can share one practical example with you. ये बात मैं आपको बता रहा हूँ 2003 या 4 के आसपास. इसको बंद कर सकते हैं भाई अब. रिकॉर्डिंग तो बंद हो सकती है ना. हाँ, ऑफिशियली इट इज क्लोज्ड. कुछ डिस्कशन. मैं आपको मैं पीएचडी कर रहा था रुड़की में उन दिनों 2003 से 5 या 6 के दौरान. तो ऐसे ही जिज्ञासावश बहुत सारी जगहों पे पहुंच जाया करते थे. तो मुझे मालूम पड़ा कि देयर इज ए